Okay, then I guess we can start. Yeah, welcome everyone to the second day of the PyHEP workshop. Yeah, as usual, please post your questions during the talk on Slido. I'll put also again the link into the chat. It would be on the agenda, but if you lost it, it's in the Zoom chat now again as well. And the first contribution today is a tutorial by Hans about how to fit models to data with iMinuit. Please go ahead.
Yeah, thank you. So this works. Do you see the slides, or do you see my notebook?
I can see it perfectly.
Okay, very good. Okay, so yeah, this is about the iMinuit library, and it's the library to fit models to data. And here are a few links. So this is a long-time member of PyHEP. So a little bit of introduction before we go into the practical part. So iMinuit is not only a front end to the Minuit 2 C++ library, but that's how it originally started. So you may know Minuit. That's a famous code in HEP to do all kinds of fitting. So whenever you do a fit, it's usually Minuit in the background that is performing the fit. So generally, it's a library to minimize statistical cost functions with box constraints, and that's what we use all the time. And what's special about Minuit is that it can also compute parameter uncertainties. It has two ways of doing this. One is profiling likelihood, and the other one is computing a second derivative at the minimum. We will explore those later. And it's a really old library. I mean, not Minuit 2, that's a rather recent library, but the technology that's behind this is from the 1970s. But it's still a test of time. I mean, has not been replaced. So that's pretty good. And yeah, so iMinuit is the Python frontend to the C++ code in root. So the code lives in root, but you can compile it without root. It's because Minuit 2 was originally a separate project that was later integrated in root, and they kept this kind of isolation, which is to our benefit. Iminut is not only a front end, so because when you have a Python code, you can do a lot of unit tests very easily, and eventually this also made us find some bugs, and so we contributed several patches also to the C++ part. So you guys also have something, get something out of this. If you're interested in the history of Minuit and iMinuit, I recommend my previous HEP talk and 2 years ago. So iMinuit is also only the latest iteration of several packages that have provided a wrapper for Minuit. Okay, so, and I said it's not only a front end to the C++ code, because it also contains cost functions. And what that is, we will see later. So this is one of the two essential ingredients you need when you do a fit. And since these cost functions are rather technical and boring, and there's not much to customize, it's a good thing to put it into a library. And I decided to just put them in iMinuit instead of making a separate package for that. Okay, so iMinuit is not the only fitting package. So actually, maybe I can make this a little bit larger. So there's also PyHEP and ZFit in PyHEP alone, and there are other fitting packages out there like I don't know, SciPy, Minimize. So why wouldn't you use it? Why would you use this one? So iMinuit is rather low level. It's rather lightweight. It's fairly hackable because it doesn't impose a lot of structure, and that makes it easy to learn and easy to extend. So those are things you might like. And on the other hand, with the built-in cost functions, it supports all kinds of fits. So you can do binned and unbinned fits. You can do template fits. You can do penalized fits, and you can even simultaneously fit different data sets. I mean, this you can also do with other libraries, but yeah, maybe not all of these features at the same time. And the simplicity of IMINT is also nice for teaching because, yeah, I mean, you can still see everything that's going on mostly. That makes it also attractive for beginners and maybe also for experts. So, for example, Glenn Cohen, I'm very happy to know or to have learned that he's using IMINT in his lectures on statistics. If you don't know Glenn, so Glenn has written, a very popular introductory book on statistics in HEP. Among other things, many other things. But there are a few things because IMINT is supposed to be simple and low level that are out of scope and that other libraries do better. So for example, there's no support for building statistical models. So when you want to fit something, you have to write a PDF yourself. You have to understand what a CDF and what a PDF is and to use this library here. And there are other libraries that also help you with this part. Then there's also no such thing as automatic differentiation. So if you heard my talk from yesterday about Jacobi, you can speed up in principle this fitting process when you have some automatic differentiation, and that's not in the scope to provide that. So you can use that if you write your model in such a way, but it's not built in. So if you want to make sophisticated limits, then you should also use something else because it is not really, there's not much support implemented there. And there's also recently efforts in making the likelihoods that we fit storable so that you can put them on the hard disk and somebody else can read it again and combine it with more data. So that's also not supported. So, and there are, of course, other libraries that provide these features. For example, PyHEP is a library that is very good for bin fits and can do very, very complicated bin fits, a la Histofactory. And it's very good for limit setting, and it can also store the likelihood. And ZFit is, for example, a library that allows you to build the statistical models more easily. And you can also sample from the fitted model. So it's a bit like RuFit in that regard. Okay, so that is all about the introduction. So let's dig into the tutorial part. So I think we should start with a simple line fit. So I import here NumPy, MapReduce, and also just for fun, this namespace class here from ARPAS, where you will see how that's useful. So I just generate some fake data so that I have something to fit. So I make 10 points here with some errors that are, 0.2, flat for all points, the same. And then I generate a line here, so with a slope of 2 and an offset of 1. And I also add these random errors here. So this funny call here is calling the normal distribution with these kind of errors, and it just samples me here some randomly displaced y positions. And then I put this is where this namespace thing comes in handy. So I can just put all these variables here into a little class that is automatically generated here by this namespace thing, just so that later I do not accidentally override my variables x and y and y. I put them in this namespace here. So, and then I can draw that. Let's execute this. So you see what I'm talking about. Okay, so that's the data I want to fit now. This should look familiar. So to fit this, I now need to provide a model and a cost function. So the model is basically what predicts the y values here for given x values for a given set of parameters. So in this case, this is a line. So it has 2 parameters, the offset and the slope. In general, models can have any number of parameters. And the cost function is the thing that tells the fitter how good how well the model fits this data. How far it is. So in a sense, it's a kind of distance, but distance in quotes, because here, in this particular case, it's almost like a geometrical distance, but in general, when we do maximum likelihood fits, it's more complicated. It's a statistical distance, so to say. Okay, so what you can do with IMINT is you can write the cost function yourself. but we won't do this here, although it's very easy and you're very encouraged to do this. But for all these simple cases, they are now already built-in cost functions, and those have a few tricks up their sleeves. That's why it's useful to use them. So if you want to fit now, you need to import the minute object from the iminute package, and the submodule cost contains all the cost functions. Then I provide the line model here. So the model is always this structure. You get the x argument is the first one, and then the other ones are parameters. So this is usually a vector here, or can be a vector in general, and a and b are numbers. So and then it returns the y values for those x and a and b. And then the cost function takes your data, the errors, including the errors, and this model. And this object you can then put into minute. So minute receives this and some starting values, because minute is using local minimizers. So you have to provide some starting value. This should be not too far away from the two values. And when I execute this, you will see some output here. In the beginning, minute doesn't do anything. It just sets up the fit. So when you look at the return value here, which prints here as a nice table, you just see the initial parameters. So you can see that minute recognized the values names here. That's not because I provided A and B here. I can also remove this and it will still work, because it reads those names from the model. So it's kind of magic how that works, but yeah, this works like almost all the time. And yeah, so it just starts with the values that we have set, and there are some errors here that yeah, we have to provide from minute, but these don't mean anything. So they are more like step size, initial step size. This you can also set yourself, but you don't have to. You can just go with the default values that iminute sets for you. So the way how to actually do now the fit is you call certain functions or methods. To be more precise, you call methods on this minute object that I just called m. So this is the main way how you interact with the fit. So all the results are stored in this minute object, and when you want to do iterative fitting or something like that, you always call methods on this. This is inherited from how C++ minute works, and how the old, well, that's kind of how the style, how minute operates, and iminute just imitates that. Okay, so let's run the minimizer. So this returns something that you can't see here because I don't assign a value to this, but what it returns prints very nicely in a Jupyter notebook. So you get this nice output here, and it tells you a lot of things. And the green color here is good. That means there was no failure in the fit. So fits can fail, and we will come back to later why that happens and how to avoid it. So you see here the minimum value of the function that it fitted, and in this particular case, minute was also able to compute a chi-square per degrees of freedom, which is 0.5, so that's pretty good. And you will see also here how many function calls it made, so that's useful maybe to see. I mean, if you start very close to the minimum, then this should be small. If you start very far away, then this will be longer, maybe more function calls, let's say. Yeah, so there's a question, can you comment on iminute's ability to estimate fit errors when the parameters are highly correlated? I will come back to this. In a later part, we will look into this. So then there's this EDM value here. That may be a bit mysterious, but if you look into the iminute docs, it's explained what this means. So this is the estimated distance to minimum. I can actually also point to this, and then you get this as a tooltip. That may be still kind of mysterious. So that's just how minute works and how it determines whether the fit has converged. So, I mean, I suggest really to read the original paper to see what this does. But yeah, the point is this number has to be smaller than this goal here. And if that's the case, then the fit has converged, or at least Minuit thinks it has converged. We will see later this not always true, unfortunately. When your fit takes a significant amount of time, there's also a time flag here. When it's very fast, and this is not there. And yeah, and here the other things here, all these green things tell you that everything worked fine. So if there's something not green here, then you should worry. You will see later a few cases. Okay, so now the output here shows the value that is fitted. So if you remember the model that we generated, A was 1 and B was 2. So it found values that are very close to that. And of course, they're not exactly the same because I added some randomness here. And then it also provided errors here. And the next thing that you can see here is the correlation matrix for these parameters. And here you see the diagonal values, which are not so interesting, and the off-diagonal ones that are interesting because it tells you that your parameters A and B are fairly strongly correlated. So the first value is just the raw value in the matrix. That's not so useful, but the one in parentheses is the correlation. So that's the value between -1 and +1. And yeah, in this case, it's close to -1. So there's another question. Minuit requires initial step sizes, which have to be guessed appropriately for the function as I understand it. Jacobi varies the step size. Can they be joined? Jacobi is not used internally in Minuit. Minuit has an internal way of computing derivatives. That's indeed how this works. So I didn't really go into the details, but what Migra does is it's computing gradients and also estimates some kind of second derivative. And when you have the first and the second derivative, you can do a so-called Newton step. And if your function is a parabola, or if the cost function is a parabola, then in principle you just need one of those steps with a perfect gradient and a perfect second derivative, and you are in the minimum of that function. And this is, of course, usually doesn't work because initially this estimate for the second derivative is very bad. And the gradient is also not perfect usually that Minuit calculates, but the algorithm is built so that even with a bad gradient and a bad second derivative, it still eventually converges to the minimum if it's not too far away from that. So I'm telling you all this to make the point that you don't have to have a very good gradient here. Migra is already built on the assumption that the gradient is not perfect. So that's why it's not so useful, I would say, to plug something like Jacobi into it. The advantage of this very simple gradient that Migra calculates is that it's very fast. Jacobi takes much more time, makes a much better gradient, but takes longer to do that. So eventually this will be better for this particular case. So there's another point. I observed that least squares needs the data uncertainties. This is the chi-square. Yes. So I just decided to call it least squares instead of chi-square because in general, the least squares function doesn't have to be chi-square distributed. I mean, the value in the minimum doesn't have to be chi-square distributed. So at least in my opinion, the name chi-square function, which is maybe what you know from PyHEP, is a little bit inappropriate or inaccurate. So I call this least squares, but eventually it's computing the chi-square. That's also why when we go back to the, where is it? When we go back to the output here of Migra, you can see the chi-square with Crusoe-Brian just computed for free here in this case. Okay, so a few other points. Minuit computes the values here to much more accurate than what is shown here, but intentionally these numbers here are rounded to use the PDG rounding rules. Those are fairly complicated and but they are very nice because they really show you only the significant digits. So you see here lots of other stuff that I haven't explained. So the main error here that is already given is the one we call Hesse error. So it's a parabolic error. It's computed by inverting the matrix of second derivatives around the minimum. So this you get almost for free all the time from Minuit. And yeah, then there are other errors that are not computed here, which are these minus errors. And so when you want, if you want those, you have to call minus explicitly. We will do that later. Then parameters can have limits, so there are no limits set, so these are empty here, and parameters can also be fixed. You will see later why that is useful sometimes. Okay, so maybe another word. So when you're really in the minimum, then your matrix of second derivatives has to be positive definite. That's just a way of saying you are in the side, you are in the minimum of a parabola. If it's not parabola, for example, in high dimensions, you could be in a saddle point. So there's positive curvature in some direction, but then negative curvature in another direction. That's called a saddle point. Then this would be not true. It wouldn't be positive definite, and that's bad. I mean, you have to be in a minimum when the fit has converged for these errors to be meaningful here. So be careful that this is green. And sometimes when this is not working, Minuit automatically tries to make the matrix positive definite, and then this last thing here, not false, this can be red. So that's also bad when you want to use the errors at all. Okay, so if you want to know more about these things, please look into the docs. So I wrote a lot of docs on all these things. Okay, so let's look at the output, the fitted values a little bit. So you can, I mean, this automatically generated large thing here can split up into parts. So when you just want to know the parameters, you can call m.params, and then you get just this part. I mean, this is actually a Python object that you can also query. It has many fields and so on, where you can read out all these values. When you want to know more about the function minimum, that's contained in this fmin attribute. So that has, for example, the chi-square degrees of freedom, the time, the number of function evaluations, and so on. So basically what is printed here, you can also access via some attributes on that. Then the covariance you get like this. So you just call dot covariance, and this is NumPy array-like matrix. It's a little bit enhanced because it knows what the names of the columns and rows are in this matrix. And yeah, for plotting here, there's also something down to that. So now I told you that if you want to have the minus errors, you have to also do something explicit, because this can be costly to compute, and but not in this particular case. Our likelihood is very, very small here and very fast to compute. So this doesn't take a significant amount of time. When you call this, you get this whole output again. But now you see there's these minus errors are now filled. And so this is an asymmetric, potentially asymmetric error. So you get two values here, one in one direction and one in the other direction. In this case, they are identical to these Hesse errors, except for the sign. Then there's this new output here that is coming from this minus calculation. So this can also fail. And when it's not valid, you will see some red here, and all these other things here. All this should be green. If this is not true, then there's some issue. Okay, so maybe you wonder. I mean, maybe you feel like, okay, let me tell you differently. So in the past, there was a time where it was stated that the minus errors are always better than the Hesse errors, and you should always report those. So nowadays, we have looked into this, especially in HCP, and it turns out that the Hesse errors are actually often at least as good as the minus errors, and they have the advantage of being symmetric and much easier to do error propagation with. So the more modern opinion is to actually, this is usually good, and only when these are very, very different from your Hesse errors, then you should report these asymmetric minus errors. So most of the time, you're actually better off using the Hesse errors, even if those are a little bit asymmetric. So when it's really, really, really important that you get proper errors, you should really investigate this more closely and also check coverage of these different error intervals. So this is just general advice that I'm giving you here. Yeah, so I mean, I told you that there are many ways of really using these objects to learn to get access to all those values. And here's just one example. I use this m-errors dictionary-like property here to get the minus errors on the parameter A. And this returns a struct that has many fields, and you can query, for example, the name. You can query this valid field. So basically, this is what is in this table here. All these values you can check and then use for further computing. Okay, so yeah, maybe, I mean, or one thing that you should also often do, or basically every time do, is to actually draw the data and the fitted model just to see whether it looks good. Because Minuit can sometimes lie. So this is what I'm doing here. So I draw the error bars again. This we have already done before. And now I also plot the model. And here I use the X values from the data. So this is convenient. Then here I have defined the model. So I can just plug in my X values here. And then I need the fitted values. And this can be done very easily by using, again, our Minuit object and calling the attribute values. Actually, this is needed. Yeah. So the star here makes sure that this array-like object is unpacked, because our model, if you remember, it got 3 arguments, and we just take the other 2 arguments here by unpacking the values, which returns something like an array. So that's a very convenient syntax. So to access this chi-square, in this particular case, you can use this fval attribute. That is, in this case, the chi-square, but not in general. This is just a function value of the cost function of the minimum, but in this case, it's a chi-square. It's chi-square distributed. You can call this a chi-square. And you also get the degrees of freedom from Minuit. So this is only, you can only do this when this is supported by the cost function. Again, the built-in cost functions support this in this case. So when this returns something that is none or infinite, then you cannot compute. I mean, then the function minimum is also not chi-square distributed. So that's the rule here. So if this is something finite, then this works. And you can plug in, for example, the chi-square degrees of freedom in your title and make a nice plot. And here I also add to the title just fitted values and the errors. So I do this with n.values and n.errors, and I plug in here the parameter names, which I get from m.parameters. And then this is just to draw the legend and the labels. So this is how it looks like. Okay, so you see, again, what I said before. So there's no built-in function in iMinute to do this plot here automatically. You have to kind of do this by hand. So this gives you a lot of freedom on the one hand, but if you have to do this a lot, you probably want to write a little function that just does this the way you like it all the time. Okay, there is actually a little bit of visualization built into iMinute since recently, and this is the so-called visualize functions. So the built-in cost functions all support this, but there are some limitations. So I cannot guess how you want to plot, for example, multidimensional data. There's too many ways of doing that. So this is only implemented for 1D data. But if you have 1D data, you can get a very quick plot just by calling your cost function, visualize, and then the parameter values. So here I plug in the fitted values, but you could plug in any other kind of values, and then this blue line would look different. So this is, of course, very useful to have a very quick plot when you are debugging. No? Then you don't want to make a production or the paper-ready plot. You just want to see how it looks like, and for that, that's the purpose of this visualize thing. That's also why it doesn't give you a lot of options to influence how this plot looks like. I mean, if you really want to do some serious plotting, you should call Matplotlib and do it yourself. Okay, so there are other ways to check that the fit was okay, and one is or built-in ways. There's another way that there's a built-in method to draw the profile. So, for example, around the parameter value A, and Minuit then draws this. So that's the cost function here. It should be parabolic, roughly parabolic, and should really have a minimum where the minimum was found. And this gray band here is just a ±1 sigma error interval. So this looks all good. You can also do this for the parameter b. And this also looks very good. This is just because this problem is here so simple that yeah, all the minimum, all the likelihood really looks parabolic. We can also look at the contour of this likelihood in 2 dimensions for the 2 parameters a and b. And this is how that looks like. These numbers here don't really mean anything. It's just yeah, the minimum value +1, +2, +3, +4, and so on. These are not confidence intervals because I called here this function draw contour. This is a fast way just to see how the minimum function looks like. And yeah, this is plotted with contour lines. Okay, so there's a few other questions. Can you pickle the M instance so you can check later all the info? Yes, you can. Since a few versions already, you can do that. This is particularly useful also to when you use the multiprocessing module in Python, and you want to return an iMinute object or you want to receive an iMinute object, this also requires pickling. And for that reason in particular, I made that. It's actually very tough. It was tough to implement because you have to somehow pickle the C++ instance in the background. Yeah, but I can be very tenacious. Okay, if you want to really have the confidence region, I hope you know what a confidence region is. This is if you make many of them and you repeat the fit with random data many times, then these confidence regions should contain the true value within a given well-defined probability. And the standard probability that people use is 86%. So if you want to have such a contour, you can also generate it, but not with draw contour, but draw MN contour. That MN is for minus. Because you have to actually run minus to do this. What minus does is really, here we only have 2 parameters, but in general we have more, and then it minimizes the function along all those other parameters and finds a certain contour in this kind of special likelihood. We call it profile likelihood. So now the meaning here of the number is really that this is a region that's containing 68% confidence. So in this particular case, you don't know what the true values are. Actually, we know because we know the true values, so they're here. So this region actually contains the true value, but that doesn't mean anything. So you have to really repeat this fit many times with random data, and then this contour is mathematically constructed so that it contains the true value in this with this given probability. That's generally true for all the errors that we usually use if you if you're a frequentist. Okay, so yeah, there was also a question: how does iMinute know how often to scan the likelihood to profile? Yeah, that goes into detail how the minus algorithm works. It tries to do this efficiently. I think one could do this probably even better. I have some ideas, but I didn't have time to really implement them. Yeah, what it tries to do is it takes the Hesse matrix. So you already have a first guess how this profile would look like if it's really an ellipsoid. And then it just does some bisection to find this this value here. The next question is it possible to get the contour data as a list? Yes, you can. So if you just leave out this draw and you just do this call, for example, and you remove the semicolon, which I always add because this suppresses the output of the function, then you get these values here and you can draw them yourself. Actually, we do this in a moment. Can you explain the difference between draw profile and draw MN profile? Yeah, I tried. So what draw contour does, or draw profile, yeah, I explained the difference here between draw MN contour and draw contour. And the same also is there for draw profile and draw MN profile. So when you just draw the profile, which I haven't done here, it gives you, yeah, I have done it here. So we could also add here MN. And if you look, I mean, it looks almost the same, but the scale here on the y-axis is a little bit different. And what happens in the background is when I just call this, it just does a scan along the direction of B and nothing else happens. So it's just evaluating the cost function as it is. But if I call draw MN profile, what it actually does is for every point here in B, it minimizes the cost function for A. And this is, of course, expensive. No? So you do a little minimization here for each point along this line. And that's why this is more expensive. But this is what you have to do if you really want to get this confidence interval. If you just want to check whether the profile looks reasonable, namely like a parabola, then you don't need this. And you can just do draw profile. So for debugging, really draw profiles what you want to use. And only if you don't trust what Minos has provided you, I mean, the numbers that they have provided, then it's useful to check draw and then profile. So in general, you don't need this for debugging. And likewise here. So I mean, the draw contour is for debugging, and draw MN contour is really when you want to publish this. No, this is you can publish this confidence region. Yeah. And of course, maybe you don't want to use our standard plot, but you just want to get the values and plot it yourself. Okay, so what you can see here from draw MN contour is that you get an ellipsoid which has this funny tilt. And that is reflecting basically what we have seen before in the covariance matrix, namely that the parameters have a negative correlation. So negative correlation means the ellipsoid is tilted in this direction, and positive would mean it would be tilted upwards. So correlations are not fundamentally bad. There was also a time when I learned that you should always construct your model so that the correlations are minimal. That's not really true, so it's actually fine. If these become very, very large, then this is usually more another issue, as we will see later when, yeah, what could be the reason why you have very, very large correlations between parameters. Someone asks also why this contour looks a little bit jagged. That's true. I mean, this is because of this finite accuracy with which Minos operates and tries to find the border of this contour. And it's also real. So, I mean, you can increase your number, the size, the number of points that is used to calculate. So you can make it, well, you cannot really make it less jaggedy. As you see, it's still a little bit jaggedy. But you can at least make it more smooth. So this is, there's some default value when you don't specify the size, which I forgot what it is, maybe 50 or 100 points. So if you want to have it really, really smooth, you would have to really dig into the Minos algorithm and then make them better. Okay, does it use linear population? Yeah, there's some kind of, yeah, not really. I mean, yeah, no, I mean, this plot here does linear interpolation, but this is a feature of MapPyHEP. So the way how it connects the points is linear interpolation, yes. Okay, so where was I? Yeah, I wanted to show you something else. So if you want to understand what this contour here basically means is, so basically what this means is if you are kind of 1 sigma-ish away from the minimum, there's a certain combination of parameter values that shift your model 1 sigma away from the data. And you can actually visualize this with this little code here. So this is just to draw the model and the line and the data again, just very quickly. We have done this before. And now I do this readout that we already teased at before. So I really get a list here of all those values A and B that are along this ellipsoid. Then I loop over them. and I draw my model for all these different parameters. So I get actually lots of model lines here. So many that I have to set the transparency very low. High transparency. So, and then you get a plot like this, which looks suspiciously like an error band. But this is not a proper error band. Don't do this. It's just for illustration what these points on the contour line basically mean. So each of them gives you a slightly shifted and tilted model line. So if you want to do a proper error band, there's a tutorial in iMinute that you can just read when you click on this link. And if you followed my talk yesterday, you may know about Jacobi already. So that's one way to do it. And another one is Resample, it's another library for me. These two you can use to make proper error bands. So I show you here how to do it with Jacobi. Again, draw the data and the model. And now I want to propagate the uncertainties that I got from Minuit, which are parameter uncertainties. But now I want to know what's the uncertainty of my model. So I just take all the outputs. The output of a model is a vector. And I just want to know what's the covariance or the error of that output. So I have to use a little adapter function here because propagate requests that the function that it propagates through just accepts one argument, and that is a vector of the parameters. So I cannot pass the x here. I have to use this with the lambda here. So this lambda just is an adapter that I can pass my parameters here as a vector. And here the vector is unpacked and the response of my model is computed, which is another vector. And that is basically what propagate needs. Then I plug in my values and my covariance, and then I get my values of the model and the covariance of those out. And to draw the error band, I need the diagonal of this. And the covariance is the square of the standard deviation. So I have to take a square root, and then I can just plot the error band like this. So I have here my x values, and I subtract to 1 sigma and then add 1 sigma, and I make it a little bit transparent so it looks nicer, and that's a proper error band. Again, you see there's nothing here done automatically, so you can easily do it yourself. But if you have to do it a lot, you probably want to write a function that does this. But there are also other ways of doing this, and maybe you find the one that's using resample more appropriate for your use case. Okay, so many more questions. There's more of a statistics question. Is there a way to get an effective degrees of freedom being non-integer when the parameters are highly correlated? So I don't provide this. I don't know how to do this in general. I don't know a good solution to calculate this. I know what you're talking about, and I think it would be very nice to have. Yeah, but it doesn't have it at the moment. So another question is, there's a way of plotting asymmetric uncertainties that come from minimums. If you get the errors, if you request the m errors, so maybe let's just do it. That's why this is interactive, right? So basically what this returns, you can use to also draw the errors. I don't have a nice example here. I don't want to do this just spontaneously, but when you use pyplot error bar, this also can accept asymmetric errors. So you just have to write a proper adapter for that. And then you can also read out and plug in your asymmetric errors. So I refer you to the documentation of this m errors attribute and how to get the errors out. So another question is, can Jacobi propagate work with a log likelihood model, or must it have an exact functional form? So Jacobi can propagate through anything. And in this case, we had a least squares function, but equally, it would have worked equally well with we are talking here about the model, yeah? So the model doesn't know anything about the cost function. It's independent of that. So you can propagate through any model in general, and it doesn't really matter what your cost function is for this. Cost function doesn't even enter here. So if you use one of the built-in cost functions, you can be sure, and I mean, if you satisfy all the requirements of that cost function, you have to read the docs. Then and you have a proper minimum, then what the covariance is returned here is really the error matrix. So, and then you can do this propagation. So that's how the cost function is important, but only in the sense of doing the minimization process and to give you the right uncertainties. Okay, so since drawing these profiles is kind of useful for debugging, I made a nice little function that does this automatically. So this is particularly useful when you have a plot with a fitting problem with many degrees of freedom. Then you can just call this, and it generates the 1D profiles and the 2D profiles for all the pairs of parameters. And I see now I used up a lot of time already, so I have to move on a little bit. But you had many interesting questions, so that was also good. So I want to say a few words about why fits fail and how to fix that. So we have to unfortunately move a little bit faster now. Okay, so one reason is if you use starting values that are poor. Poor means far away from the two values. That's, I think, the most common issue when you start fitting, that you don't know really how to find good starting values. And the reason why this fit fails is, I mean, in general, we fit maximum likelihood, and the likelihood is a product of probabilities, and then you take the probability of that. So if your probabilities are 0, because your parameters make it so that the data is very far away from where your PDF is defined, then you just get 0, and the logarithm of 0 is minus infinity, and then it doesn't know which direction to go. It looks like wherever it goes, the function is just minus infinity, so then it cannot really find a minimum. So that's why you have to start reasonably close to where your minimum is already. Then another reason, more subtle, so even if a function is not just minus infinite, if you were very far away, then if Minu just does a small step in one particular direction, the change in the curvature of this function may be so small that it really doesn't recognize that it thinks it has already converged, although it hasn't. Okay, so to illustrate this, I show you here. Now this is an unbinned maximum likelihood fit. I generate some normal distributed data, and then I fit the normal distribution. By the way, I use the normal distribution here from numberstats, not from SciPy. Numberstats has faster version. Unfortunately, I mean, the SciPy statistical functions are great, but they are very slow. So if you want to have something faster, go for numberstats. Yeah, okay, so it's a normal distribution, so it has a location and a scale, so mu and sigma in our language, and that's what I fit, and I use a starting value here. So this random number generator generates a standard normal distribution with a mu of 0 and sigma of 1. So I also set the scale to 1, but the location here is set to 50, just to make it really bad. And you see now that fails. And you see this is not green, it says the minimum is invalid. You also see that the EDM value, there's none, that's bad, not a number. And yeah, okay. And interestingly, Hesse says this is okay, and that's wrong. No, Hesse should also say that computation failed. As you can see, the errors here are also none. That's clear. If you have none to start with, any computation will also give you none. This is actually a bug in C++ Minu 2, and we should fix this. And this is also a shout out to you. So when you see things like this, don't just shrug your shoulders and say, okay, software is just weird. Please report this, because I try to fix all these things. So, I mean, I think this should be, when errors happen and where you develop, a lot of errors happen. So the library should give you very good feedback on what the errors really are. And something doesn't work, it should give you a proper error message. So I think it's a great way to contribute to the hacker shop, just reporting all the errors that you find with simple reproducers, so I can actually understand and figure out what's going on. So just to illustrate why this is happening, so our model is over here, and our data is over here, and just for numerical reasons, the PDF starts to become 0 here at the value of 30, so about 20 units here away from from the location. And there's also, you can see this more explicitly here. I just call the PDF or with a mean of 0 and sigma of 1 at several values, and see at 1 and 10 it's still defined, and then for the other far away values it's just returns 0. It's just because floating point numbers cannot be smaller than 10 to the minus 333, I think. And these numbers are smaller, so it just returns 0. Okay, so we can fix this just by using a good starting value of 0. And then you see, okay, now it found reasonable values, everything is green, so this is fine. So how to get better starting values? I mean, there are many ways. So, I mean, one way, if you have simulation, you can maybe just use the starting values from simulation, even for your data, if you have scaled the simulation appropriately. And other ways is sometimes you can do a simpler fit and then use this as a starting point for a proper fit. So, for example, these square fits are generally very robust, even when you are far away from the maximum. And you can start with this and then use a maximum likelihood fit as an afterburner. The reason why you can't use it just least square fit all the way is, at least for Poisson distributed data, which we usually have, this is an approximation and you really have to use the maximum likelihood theorem. Okay, so this problem here is not only academic with this Gaussian that I fitted, but you can also have this in more practical situations. We do a lot of signal plus background mixture models. So I generate here some normal distributed signal and an exponential background, and just plug this into my namespace here again for convenience. And here I plot you this. So this should look familiar when you do ING physics. Now you want to fit the peak here. The background is usually not of interest. So we do an extend bin fit. And if you don't know how this works, you can always ask the help. And the help is very extensive. It tells you how to provide the parameters and how the model has to look like and so on. So in this case, our model looks much more complicated than before. So again, the x values are provided here as the first argument, and then it has 5 parameters: the yield of the signal, the mu of the Gaussian, the sigma of the Gaussian, the yield of the background, and the slope. I mean, this background was an exponential, so it only has a slope parameter and an amplitude. And now I use here the truncated normal distribution and truncated exponential because my data is also truncated, so this you often forget. But I mean, here I cut at the values, so I mean, that's also what you usually do. I mean, this is an invariant mass distribution. You only look at the slice, you don't look at all possible values. And then the proper way to handle this is actually to also use the truncated distributions for fitting. Often you can get away with not using the truncated ones, but in principle, this is the proper way. Now we need a different cost function, this extended bin likelihood, because we want to fit bin data now. And it's extended because we don't fit fractions, we really want to fit the yields. Because, yeah, this is not a fraction, it is just an integral over the PDF. And I provide the bin counts and the bin edges and the model, and then this gives me my cost function. And I plug this into minute, and then I have to choose starting values. And here again, I chose poorly because my mu is here at 5. I mean, you can see already by eye that the mu has to be around 0.5. So I'm factor 10 off. And that's why I get here again my not a number and everything is bad. And the reason is if I just call the function really at those points, it already returns none. So I mean, there's no way that Minuit can recover points. Okay, the solution is again just to use better starting values, of course. And but another thing that is important here, and why I choose this example, here we have now parameters that we really need to constrain. So, for example, the sigma parameter of the normal distribution, it cannot be negative, and so you have to provide some limits. And this is done with this limit attribute here. You give the names here of the parameters, and then this is a one-sided limit. And this you really have to do. I mean, yeah. I mean, if you provide a negative value of sigma, or Minuit just stumbles into a region where this value is negative, this is just not defined, and then you will get none for sure. Also, the yields, they have to be positive, cannot be negative, and so on. So I have to really move up because, yeah, we won't have time for questions. But I want to show you a few more things so you can also visualize this. In this case, I seemingly got a good minimum here, but the chi-square was bad. It's 4.5, not close to 1. And when I visualize the result, I can see also why. I mean, somehow the background here was not fitted properly. And that's why you should always check also this the fit result. And I can now also use this floor profile to see what's going on. So around the signal yield, it looks actually quite nice. And when I look at the slope, I see where the problem is. So this is not a minimum at all. This looks like a line. No? So this is not parabolic. So this is bad. I mean, the problem is here, why did Minuit say it's converged when this is obviously not the case? So just because this EDM criterion is also not perfect. Maybe we can fix this. I have some ideas how to do this. Okay, so to solve this, we have to also put some stronger limits on slope. Before it was just has to be positive, and now we say it has to be between 0 and 2. And when we do that, we get a good result. So now the chi-square is 0.9, which is very close to 1, and we are happy with that. We can visualize this, and it looks okay. And we can draw the MN matrix. This takes a moment. Gives you a nice progress bar. And then you see all these profiles here, which just look beautiful for this case. Now you see these are not perfect ellipsoids all the time. This looks more like an egg. That's how it is. So the last reason why you can, okay, I guess I have to skip this. I mean, another reason you can have an ambiguous model. Okay, but very briefly. So this would be one example where you have too many degrees of freedom. So this is a line, but you have provided here 2 offsets. And when you have that situation, I can just make B arbitrarily small and compensate by making A arbitrarily large. And this creates an ambiguity, 2 perfectly anticorrelated parameters. And when you try to compute the Hessian, this still works, but the Hessian doesn't have full rank anymore. And when you try to invert this cannot work. I mean, if you try to invert a matrix without full rank, you don't get proper errors. And so I just execute this, but we have to skip all this because I'm running out of time. There are ways to fix this. You can apply some penalties to resolve this. You can fix the parameters that are superficial. And yeah, just to, it's a very last thing. I wanted to show you the interactive mode. That's also very useful. So I just to play around with this. You can just, when you have a 1D fit, you can just call Minuit interactive and then draw some sliders and see how the model changes. And you can fit it also, or you can optimize certain values and then just change the others and see how this changes the fit. That can be very educated. This is very jaggedy here in a Jupyter Notebook. When you do it in VS Code, it's very smooth and nice. The very last thing I have to skip over is there's also a way to do a Barlow-Beeston template fit recently. A template fit is when you don't have a parametric model, but your model is also a random histogram that you got from simulation. You can also now fit this. There was a cost function added for this. And yeah, I mean, now your model also has errors because it's a histogram, so it has statistic errors. And these Barlow-Beeston-like methods, they include that error in your fit. So when you fit this with such a histogram model, you get additional uncertainties that come from the fact that the model is not well defined. Yeah, and I suggest to read a little bit here more about the points that I made, all these nice references where this is explained better. You can also do this interactively, of course, and see how things change when you change the yields. And with that, I would close. Sorry, one minute too long. If you want one more, please look into the tutorials and the studies that I have in iMinute.
Okay, thanks a lot for this very nice, very useful tutorial, and also thanks for staying in time. Since we started 2 minutes late, I think there's time to maybe answer one or two more questions on
great.
Slido, and then we can move the rest of the discussion to Slack.
Okay, so maybe Eduardo, you can comment. So you said at some point, what would happen if you try to plot at this point? At which point?
Right. Yeah, I mean, when you gave it a completely different new, completely offset, so there was no way you would have convergence. And then I was wondering, yeah, a few bits before. So if you were trying to plot before actually, but when fit was not converging everywhere. Yeah, above this thing basically. Went fast, right? I think it was roughly here, right? Exactly. Well, when you had a none, sorry, when Hesse was saying okay, but you actually had a none as a value.
Yeah, I mean, then it will just plot nothing because when it tries to evaluate the model, since one of the parameters is none, then the model would also return none, and then I mean, Matplotlib just doesn't draw anything when it has none values.
Okay, of course, yeah.
So that wouldn't be very helpful. You would just see the data, but no blue area. So.
Yeah, exactly. I was not seeing a way of plotting it, but just wondering how that would work out. Okay, thanks.
And there's a question, Minuit, whether it supports unbinned fits with data with weights. So not unbinned fits, but when you have bin fits with weights, that's supported. And unbinned fits with weights are complicated, so we don't support that right now. The reason is because you cannot, the way how Minuit calculates the errors doesn't work for an unbinned fit that's weighted. You have to actually use a different way of calculating the uncertainties for your parameters. That's not supported by Minuit. So maybe we will support this in the future, but it's kind of a little bit out of scope of what Minuit can do.
Okay. Yeah, then I think maybe we
I guess
move on with the next presentation.
Yeah, I can just answer more questions later in the chat.
Yeah, thanks a lot. Yeah, we will post them on Slack and can.
Yes, Slack better. We'll move the questions to Slack.
Yeah. Okay, then we will have the next presentation by Jayjeet. Please correct me if I mispronounce the name, about Skyhook and how to manage columnar data already in the storage. Please go ahead.
Hi, yeah, sure. Give me 1 second. Let me try to share my screen. Okay. Slideshow. Okay, just quickly checking. Can you see my screen and hear me?
Yes.
Okay, awesome. Yeah, so hi everyone. I am Jayjeet, second year PhD student at UC Santa Cruz. And today I'm going to talk about our work on Skyhook, managing columnar data within storage. And basically, I'm going to talk about how we plan to use it to solve data management problems that we see in the high energy physics world. So let me start by defining the broader problem that we are trying to solve. Data scientists are required to perform a lot of exploratory data analysis, which often requires viewing a data set in different ways. For example, this case is most evident while working with derived columns or a subset of columns. Currently, doing this requires copying the data set multiple times, leading to increased overall analysis time, increased space overhead, difficulty in tracking the different copies that we create in the process, thus overall making the analysis workflows much more complex and difficult to maintain. To fix these problems, we envision an ecosystem starting with what we call a data repository, which is very similar to what we see in a Git repository for code. In this case, our data is stored in a data lake, and with the help of different open source tools, we aim to achieve features such as version control, time travel, rollback, and schema evolution. These features allows us to keep track of how our data evolved over time. We also aim to support views that solves the problem of having to copy the data multiple times just to be able to view the data in different ways. We also want to be able to perform complex compute operations on our datasets and perhaps join them in a distributed fashion. Finally, we want to reduce the data movement across our entire stack by trying to process our data in place as much as possible. We want to do all of this, but in the context of HEP data, which comes with a little bit of challenges. For example, HEP data is usually huge in size. It has large number of columns, and most of those columns have embedded values. This kind of a complex schema makes it unsuitable for HEP data to be stored in relational database management systems, which mostly prefer a flat kind of schema. Also, since the high energy physics community is largely invested into using Python as their principal programming language for analysis, we should be able to provide Pythonic interfaces to high energy physics data scientists while being able to leverage all the modern data management tools and frameworks that we have, which are not always written in Python. As we see, most of them, like almost half of them are written in like Java. But we see that the vision that we saw seems to fit really well in solving these challenges of HEP data. So to bring our vision to reality, we have designed a solution which involves intelligently integrating different pieces of modern data management and processing technologies to create an end-to-end data processing ecosystem, which is catered towards HEP data scientists. Now I will describe our solution one by one. So since our solution involves different systems, we need, at first, we need a zero copy in-memory data format that eliminates serialization costs while moving data back and forth between different data processing systems. So in order to reduce the data movement across the entire ecosystem, we need to use an active storage layer that allows performing tasks like decompression, decoding, filtering, and projecting the data within the object storage layer itself, thus freeing up the clients for doing important processing tasks. Since our datasets are huge, we need to be able to process our data in parallel using a cluster of machines to finish the analysis in reasonable time. Therefore, we plan to use distributed compute engines that allow distributed processing of data using semantics like MapReduce, bulk synchronous processing over modern communication technologies like MPI, UCX, RDMA, etc. Next, to be able to realize our vision of creating data repositories or a single source of truth for our data, we need to use one of the most important pieces of the stack, which is our lake housing engine that supports an open table format, that allows doing data warehouse operations like version control, time travel, rollback, and schema evaluation over data lakes. Since different data scientists have different languages of choice, we need expressive query interfaces that can generate standardized query plans, which are acceptable by most popular data processing systems. So that's the high level solution that we have designed. Now we have selected some technologies, some open source technologies that we plan to use in implementing this solution. So our implementation has 3 layers. So there is a storage layer, which is basically a distributed object storage layer. Then there's a compute engine for doing all the data processing and compute operations, and finally there is the client where the data analysts interact with the entire system. So on the storage layer, we use an active storage layer where which is in our case is Skyhook. So in Skyhook, so basically what is Skyhook? Skyhook is a plugin to the popular programmable object storage system Ceph, which embeds Apache Arrow libraries for being able to filter and project data directly within the object storage layer of Ceph. So in this way, using Skyhook as the storage layer, we can filtered the data very early in the stack, and thus immediately reduce the data movement across the entire across the entire stack. Next in the stack is the compute engine, which for which we are looking into technologies such as Cylon, which uses bulk synchronous processing over MPI. We have our good friend Dask. Also, there is a new framework out of Facebook called Velox that mainly focuses on efficient vectorized processing of data. So we can use any of these engines according to our choice and according to the different compute operations that these engines provide. Next, to realize the lake housing vision, we use the Iceberg, which allows doing time traveling, schema evaluation, and transactions. Basically, all the data warehouse stuff over our Skyhook data lake. And on the client side, we have query interfaces such as Apache Calcite and IBIS, which basically takes SQL queries and also SQL queries in Calcite and Python queries in IBIS, and translates them to substrate plans, and then feeds those substrate plans to the compute engine, which then interacts with the storage. So how this works is, from top to bottom is our data analyst uses frameworks such as Calcite or IBIS to write a query in either SQL or in Python. Then the query is compiled to generate a substrate plan. So substrate is basically a flat buffer style format, which is also developed by the Apache Arrow community. And it is used to specify query plans that all popular compute engines can recognize. So once the substrate plan is there, it is sent to the compute engine. Then the compute engine decides what part of the plan to execute on the engine and what part of the query plan to be offloaded to the storage. So it chops up the query plan accordingly and executes the query plan in the storage and in the engine, and finally gives us back the result in the form of arrow tables. So yeah, last slide showed the client using IBIS in Python, writing queries in Python, and this slide shows like the client using Calcite, writing queries in standard SQL. Quickly going over the Skyhook architecture. So basically, Skyhook has an object store at its bottom, which embeds Apache Arrow libraries, and on the client side, it uses the Arrow dataset API. So while writing files, the user just writes files to a safe file system, and while reading, it just skips the file system layer and directly uses the storage interface libredos, where it converts file names to object IDs and invokes Apache Arrow functions over the objects directly within the object storage layer. And all the distribution of the compute operations to the objects are taken care by the safe redundancy layer. So currently we have upstreamed Skyhook into Apache Arrow, and also we are working on improving Skyhook's performance by trying to see if technologies such as RDMA can improve the transport between storage and the client. Yeah, so that was the end of my talk, and this work is supported by the National Science Foundation and the Center for Research in Open Source Software at UC Santa Cruz. Thank you all for listening. If you have any questions, please ask me on Slack or just send me a mail to my email ID. Yeah, that's it. Thank you.
Okay, thanks a lot for this very nice overview of this package. Unfortunately, we are running a little bit over time, so we should probably also take my question to Slack and continue with the next presentation, which is by Eduardo about particle and the decay language packages.
Can you see me and hear me okay?
Perfect.
Yeah, the slides are being broadcast, right?
Yes.
I put it bigger. I hope it's big enough, but otherwise let me know. All right, thanks very much. So yeah, I'm going to talk you through in this lightning talk in a few minutes, have a kind of a hello world to these two packages, which are very specific, HEP specific, namely particle and decay languages. So by the way, I have a bit more information that would fit in 10 minutes. So I put further reading in a few places, and I'll skip a few of those examples that maybe are a bit more advanced. So this one is a bit like an internet. So I'll just run it, but I will start straight with the description of the particle package, which is the first one, mainly the core of this presentation. So particle data in short is particle data group, PDG, particle information, and MEC identification codes. And the main reason for this is some of these bits of information are often needed by all kinds of users in various occasions, and it's just nicer to provide something that does it quote unquote the best way possible, rather than having everybody trying to hack around for essentially the same piece of work. That's in short what I'm describing here in a bit more detail on the motivation for the particle data and in the MC identification codes. Again, because these are used by simulation packages, several ones. Sometimes they don't have the same IDs to describe or identify the same particle, and that's a bit annoying. So you want a way of exchanging and knowing what exactly is what in each Monte Carlo program. And of course, the central one is the PDG particle data group numbering scheme. That's what the package is about. It's essentially a Pythonic interface to the particle data information, and MC stands for Monte Carlo, right? Simulation identification codes. That's what I'm putting a bit more in detail. So I'm going to browse you through some of the main classes and then show you how you can programmatically query all the information that is contained in the package. So this is still all text at the moment, but so you see that the PDG ID class, which is the main one, and then you see already two examples of giant tree or Pythia with its own numbering scheme, so its own IDs, and you have a few converters that you can play with if you want. So starting with the PDG ID class, let me just clearly import it from particle, and you can just create a PDG ID for 2011 in this case, which is a positive pion. So no big deal. It just shows that it has created a class as in anything in C++ in Python. Now, if you wanted to go randomly creating anything, you actually see immediately in this case that is PDG ID is an invalid number. So you would not be surprised later on by that. And more usefully, you have a bunch of properties you can ask this PDG ID class, and the same functions or properties in this case can also be used as standalone functions. So if you want to query here whether this PDG ID, the pion corresponds to the meson, which is the case for the pion, that you can either do as a property of the ID instance or a standalone function. Nothing more. Now, if you wanted to know what all the properties that are available in this PDG ID, then you can query with info, and you have a very long list telling exactly what are the typically yes and false for kind of has or is types of functions, but you also have some other ones such as the charge, the is valid, of course, at speed, and so on. So I'll give you further reading on this if you want to, if you are interested at some point in translating between Monte Carlo programs, and you would want to use PTIDs or giant tree IDs, which are a little bit old by now, but still use sometimes. Then you can play with that. I'll let you do that. So I'll skip this thing. You can see you have various converters. Okay. So the other central class in the package is the particle class. So this is where you start to be able to programmatically do more things. So here I'm going to say I'm going to create a particle from its ID 2011, which we know is a Pi plus. So here it's just telling me exactly that, and you can have a nice display immediately with the Greek letters for the notebooks, right? Now, even more useful if you want to then go beyond that and you want to query all the information that are behind the scenes in our data files that have already massaged some information downloaded from the PDG, which is something that you will have to massage yourself by hand, and that can be quite painful, tricky, and we provide quite a lot of enhanced information for that matter, actually. Then you have these two main functions called find all and find iter, which is the first one gives all the search candidates that match some queries, some properties specified, or else you can iterate over those. So this is how you would go if you want to find all that that match JPSI. In this case, you only have a one item list, but that's where it is there. So it gives you a list of everything that has matched. Now, if you wanted to iterate, and here I take the first item of the iteration, it only finds one particle because I'm actually specify the full name of one particle. I know that. I used to the standard phi, then it gets you immediately the particle. As if you were to check the type, you would see that it indeed is a particle. Now, at some point, you can start becoming a bit more fancy rather than just giving a name. So, for example, if you wanted to match and try to find all the pi type of particles of negative charge, you could just specify here the name pi, and then say charge I want -1, so you would get all the negatives, right? And if you're doing that, you would get all the charge conjugates. So nothing to worry about. And when you really want to start going fully fancy, then you can instead of providing these properties in the call, you could provide a function that allows you full flexibility. So I'm going to do that. I'm just taking DV units from this little HEP units package. I mentioned at the very top as an internet, so you can go and know more about that. But here you see it's broken, but essentially it's a one-liner where you say I want the PDG that has bottom flavor charges equal 0 and the mass is between 5.2 and 5.3 DGV. That's typically the B-meson, and that's why you get here. I have not specified any flavor rather than just say I want flavor bottom, so that's why you have both the particle and the antiparticle. You see 511 and -511 for the B0 and the B0 bar. And you have a nice printout by default that gives some basic properties. Yeah?
I have around 2 minutes left in Valo.
Okay, all right. So you can go quite fancy. The one I wanted to show, I didn't start 8 minutes ago. Yeah. Okay. Right. So you can go really fancy and see in a one-liner again. If you want to say pseudo-scalar charm reasons, you could implement a trivial lambda function that would provide you everything. So you can go a bit fancy, trying to describe the particles. You see in notebooks you can get nice descriptions and so on. So I'll let you play with that. You also have literals if you want to pragmatically work with several particles. So that's again further reading, because as I said, I was provide far more than you could possibly see in 10 minutes. And again, if you want to know more about the data files, then you can look into this. Just showing one example here, using the exploiting tabulate package. Then you could export all the information in the dictionary, also in a list, and then use tabulate to have a nice overview of a bunch of particles in a tabular format. So you can also do it in HTML, etc. Okay, RST if you want. We name it for any kind of information or documentation that you'd like to do. The data package is decay language. So this really is as very important in flavor physics to describe those so-called .dec decay files that are used in MC programs such as EVTGen to describe the decay chains of any possible particle chain you might have. So you can programmatically do that. I'm going to give you an example here of a decay file where you see that there are two decay files, the two trivial decays specified with a bunch of aliases. If you don't know these things, of course, I'm not going to spend 10 minutes explaining what the files is, but you can more or less read that he's talking about the decay of one particle in two here, and so on. He also has some decay models. So if I take the main class, which is a decay file parcel, and I do that on the LHB master file, it's a big file. You'll see that it contains more than 500 decays there. It's 11,000 lines long. So you can parse it. It's not too long. It takes about 2 seconds typically. And then you can see that, yeah, it has parsed 506 decays in there. And you can have all the combinations, of course, that will give you thousands and thousands of combinations. So you can go around and read. You can parse all the information. You can also do it from a string. You can do multiple files at the same time. So you read like a combine if you want. And then more usefully, let me just parse these things. I need that information. You have all kinds of properties that you can acquire all the information inside the file. More usefully, you can also build the decay chain. So I want to know the decay chain for the DD+, for example. This is internally stored as a dict. And of course, it's even more important if you want to see what that looks like visually. It's much better than looking at the data. It becomes very quickly and comprehensible for the human eye, and you can do all kinds of things. So you can see that you can be very verbose if you want, again, on how that little file can be parsed and provide all the information. These are the branching fractions, probability of the decay modes. So you can do all kinds of things. You can specify, you can say, I want to switch off a branch because it's looking too complicated. So I put effectively a bunch of particles here stable. So you only see the first bit here, and so on. You can do charge conjugation, you can save it. I give you some handles on how to do that directly with GraphViz behind the scenes. This is further reading if you want to start looking fancy, because there are a few cross checks for no nonsense inside the parser again, so that I'll let you play with that. And the last point is, I finalize here, you can also build decay chains themselves programmatically. So you have a bunch of 3 classes, basically decay modes, decay dotted and decay chain. So you see you are building by hand what you could find in a file, but you can do it programmatically. So you can do all of that, and you can get back all the information as before. And of course, visualize it as well as with the results of the file that you have done. And of course, if you flatten the whole chain, then it just gives you you see here all the decay chain, well, actually here. So you calculate the product of the branching fractions to give you the full visible branching fraction of all these decay modes. So a pi 0, pi plus, pi minus, and 2 gammas. And that's it. I'll stop here to avoid going more than an enlightening presentation. But I thought I would give you a hello world and a bit more information in case you want to play with this. Thank you.
Okay, thanks a lot, for this very quick overview of a package with lots of options. So definitely should look more into this. Unfortunately, I think also here we should move the discussions to Slack and continue with the next presentation, which is about phase space and also decay language again, by Simon.
Yes,
So,
I'll
go ahead.
will try to share my screen as well. Is it visible now?
Yes.
Okay, perfect. So yes, thank you. I'll talk about phase space and the decay language, a bit more about decay language as well. So what I'm been working on is a package called phase space, which is a package built in Python and using TensorFlow, which you can use to make very simple phase space generations and simulations of that. And the new feature that I've added to this package is the possibility to load decays from decay language so that these 2 packages interoperate quite well. And also it makes it easier to, I've also added some features to make it easier to specify resonances and customize these mass functions and which masses that certain particles should have. And if you want to try it out yourself, there is this Jupyter notebook that you can try out. There are some problems with Binder right now, so I'll fix that after the talk. But you can also pip install this package with the from decay flag. So the main package here is phase space, and the newly added feature is the gen multi-decay class, which I will talk a bit about. But before that, I will have to talk about gen particle, which is another class in phase space, which can be used to simulate these decays and the phase space generations. So you can specify a pion, for example, with this gen particle class, and then you specify the mass here as the second argument. And then you have some other particles as well, like a kaon, a k star, and a gamma. And then you can specify this dot set children and pass in some gen particles to that as well. And this will then, that way you will build up a decay that you later can simulate. And the way you do this simulation is by running the .generate method, and you specify the number of events that you want to simulate. And the output here will be weights and particles. And weights here will be just a tensor of numbers, and particles will be particles here will be a dictionary containing tensors, which will be 4 vectors of the particles that are decaying. So the problem with this is that it works quite well, but it's you can't simulate particles that decay in many different ways. So when you have multiple decay chains for a single particle. So this is something that I've added. So first we will just parse decay from decay language, as Eduardo showed before. And this will look something like this. So we have a pi0 decaying to a gamma gamma, or E plus E minus gamma, etc., with some branching fractions here. And then what we can do is that we can take this parsed object, which is just a dictionary, and pass it to the gen multidecay.fromDict class method. And now you have a gen multidecay object, which you can, which in turn contains a bunch of gen particle objects, which will do the heavy lifting of running all the simulations. So it's a wrapper around that. Now, just like a gen particle object, you can run the .generate method on this object, and then you will have a bunch of simulations which will give an output. So here around 10,000 simulations, and 9,881 of them were probably this decay, and then there were a few more of this decay. And you can see that the branching fraction here roughly matches the number of simulations that we got out here. Now, this is great. Now we have some kind of layer that works as so you can just take a decay from decay language and then pass it directly to the phase space package, and now they work very well together. Another thing that I've added is changing the mass settings for these particles. So when you have a particle, you what it does is that it automatically finds the mass using the particle package that also Eduardo talked about. But you can also specify which mass function it should have for more customizability of the resonances. So you can, for example, set if it should be a constant or a variable mass by specifying the tolerance, which you can pass into the gen particle constructor. This way you can have some particles that decay with a fixed mass or a variable mass. You can also specify which mass function it should be. So let's say that we have this kind of decay of a D star plus, which decays into some other particles. Now the default mass function that we will use for a particle with for resonances will be a relativistic Breit-Wigner function. But if you want to change this to a non-relativistic Breit-Wigner or Gaussian function, you can do that by specifying the Z-fit parameter. And so you have this dictionary that you got from decay language. And then if you add a Z-fit parameter to it, so here I will not explain everything, but here you have a pion decaying to, for example, the gamma gamma, as mentioned before. And then you add this Z-fit parameter with the Gauss setting. It will use a Gaussian function for the mass instead of a relativistic Breit-Wigner. And then you can pass it to gen multi-decay as before. Now this could be quite tedious if you want, for example, if you want the pi0 to always decay with a Gaussian mass function and not just when it decays to 2 photons. You would have to specify the Z-fit parameter for every one of these decays, which is quite tedious. So instead, you can add the particle model map parameter to the gen multi-decay constructor, and then you can specify that pi0 should always decay with a Gaussian mass function. Another thing that is quite nice if you want to use the Z-fit parameter is that you can specify when you make this decay language dictionaries, using the decay mode and decay chain objects, as Eduardo showed, you can specify the setFit parameter quite naturally in this construction process. And then you can pass this, convert it to a dictionary, and then pass it to gen multi-decay to create an object. I'm not sure if I have time, but you can also specify custom mass functions. So if you, for example, in phase space right now, there is the Gaussian, the non-relativistic Breit-Wigner function, and the relativistic Breit-Wigner function that you can use for the distribution of the mass for a particle. But if you want some other distribution, you can even create it yourself with with a function, and then you can pass this to the gen multi-decay constructor, and then you can use custom mass functions so that you really want to, so you can really extend it and customize as much as you want around this these simulations. But the basics are quite easy to simulate. So in summary, phase space is a package for phase space simulations using Python and TensorFlow as the computational backend. And this newly developed gen multi-decay class, which I've introduced to phase space, can be used to make it easy to load and simulate decays from decay language and make these packages work together quite nicely. Additionally, you can use gen multi-decay to customize resonances and setting the mass to be constant or variable, or having a certain mass function, or even specifying different mass functions for different decay chains of the same particle, and even using custom mass functions. So it's quite flexible, but the basics are quite simple, and it works just out of the box when you want to do simple simulations. So I think that's about it. And if you have any questions, I'm happy to answer those. Thank you.
Okay, thanks a lot. Also, thanks for staying within the 10 minutes. Currently, I don't see questions on Slido, but yeah, please, if you have any, continue on Slack and ask any questions you have about decay language and together with phase space. That would bring us, I think, to the last contribution of the session, which is a tutorial about constructing HEP vectors and analyzing HEP data using vector by Saranj. So please go ahead when you're ready.
Thanks. Is my screen visible? As well as, am I audible?
Yes, I can see it and I can hear you.
Thanks. Okay. Hi, everyone. I will be talking about HEP vectors and a simple HEP pipeline using vector. So right now we're here at in today's PyHEP. So you can run this talk on Binder from this, and you can visit the GitHub repository. So you can clone the Jupyter notebook locally and run it locally as well. I'll be talking about vector today. So a lot of information in this notebook is derived from the README of vector as well as the documentation of vector. So you can visit those and you can start it if you like the project. And we're also organizing a hacker shop related to at the end of PyHEP, I think on Thursday and Friday. And we have vector as a project there. So you can visit, let me see where it was. You can visit the dashboard at scikit-HEP. So if you go to the scikit-HEP organization and navigate to the project, you'll see a dashboard for the hacker shop where we've listed some beginner friendly issues that you can pick up when the hacker shop starts. Okay, that brings us to our talk. So this talk is authored by Henry, Jim, and me, Saranj. I am an undergraduate at University of Delhi, and I'm not a physicist. So I like maths and CS, but I'm not a physicist by in academia or by profession. So I might not be able to handle the physics related doubt, but I'll be very happy to take up vector related doubts. Here are some quick links for the project, and I'll try to wrap it up in the next 20 minutes so that I don't take up the break time. Table of content. So introducing vector. This was also introduced by Jim in yesterday's talk, but he could not complete his talk due to time limitations. I would try to cover up those things as well, but I would not be covering uproot and awkward in that much detail. So vector allows a user to create 2D, 3D, and Lorentz vector, and it was initially created for HEP, but it is not limited only to HEP. So you can create 2D and 3D vectors or arrays of vector and perform any mathematical calculations on them, not just limited to HEP. The goals of this talk would be to introduce vector and its backend. So first introduce the vector and its backend, then introduce vector in a data pipeline, which would be using uproot, scikit-learn test data, and awkward, and see how all of that integrates. This is the setup that you can go through. You can we recommend running it on Binder, but you can also use Google Colab or run it locally. Okay, let's start by importing vector first. Vector comes with 3 backends: the object backend, the NumPy backend, and the awkward backend, and then number-based backends of object and awkward. So object type vectors can be created using the obj constructor or using the class method. So we have different classes for different dimensions of vectors: so vector object 2D, vector object 3D, and vector object 4D. I will be talking about them in a minute. You can use the class methods, which go like from underscore and the coordinate names ahead. So if you don't want to specifically include coordinate names in the constructor, for example, in vector.obj, we need to pass the coordinate names as well. You can use class methods for that. Using vector.obj and passing the coordinate names as well as coordinate values creates 2 vectors. Like passing them twice, using the constructor twice, creates 2 vectors here, both object types, and they inherit everything that a vector can do from the vector superclass. Similarly, you can create the vectors from class methods, and it works completely as it works with the obj constructor. And similarly, you can create momentum vectors by specifying momentum coordinates inside the constructor vector.obj. I think you cannot create momentum vectors from the class methods yet, but we are working on new constructors, so that might be possible in the future. And like, for example, if you vector knows when you want to create a momentum vector, if you specify only a single momentum coordinate. So for example, if I specify px and y, it will automatically create a momentum vector and not a normal generic vector. It created the momentum vector again. Going through the inheritance and superclasses of vectors. So it is best summarized using this graphical representation that is available in vectors repository. So every vector or every backend that you see is a subclass of the vector class and the subsequent dimensional class. So for example, vector 2D, vector 3D, and vector 4D. So the vector object 2D, and here you can replace object with any backend. So for example, NumPy or awkward. And the vector object 2D will be inheriting from vector 2D, which would be then inheriting from the vector class. We can see that this in action here. So if we just print out the types of these vectors, we will get the object classes, which are, okay, let me clear these cells first. That would make much more sense. Okay. Go ahead. So we have the vector object XD classes for each type of vector, and the backend module was recently made public. So a user can extend these classes if they want to. So all vector classes are subclasses of vector. Every backend has its own vector backend XD class. So for example, vector NumPy 2D class and vector object 3D class, which is a subclass of vector backend. So vector object and vector NumPy. And all 2D vector classes are subclass of vector 2D and so on. So 3D classes in subclasses of vector 3D and so on. They should output true, as a vector 2D is a subclass of vector, vector 2D, object, and object 2D. Similarly, we can do for planar, spatial, and temporal classes, which are available here. And momentum vectors work the same way as the normal vectors. The addition here would be that it would also be a subclass of momentum vector class and momentum object 2D vector class. Additionally, we can the coordinate classes are also subclasses of the top level azimuthal, longitudinal, and temporal classes, which can be seen from here. So there are no assert errors here. So that means a vector 4D temporal will be a subclass of vector. The object would be the class would be the object that belongs to the class would be a subclass of temporal, temporal tau, temporal object, and temporal object tau. We will come to this back in a minute. Then we have vector methods and properties. So a vector introduces a lot of methods and properties. So a whole list of these methods and properties are available in the README file of vector. Let's quickly create a vector 3D object. And a good way that or a way that I prefer to look up these properties is by clicking tab after typing up the object name, and it shows up all the properties and the methods that can be applied. Another way is to go through the documentation, or you can click on this link and view the complete list. So let's say we want to gather the azimuthal coordinates. We'll start by obtaining the azimuthal object. So if here I click tab, there should be an azimuthal property here, and that can be used here to generate an azimuthal object, XY object. And let's say we want to take out the elements of this. We don't want it to be a class object. Rather, we want a tuple of elements. So the best way to go about this would be to read the documentation of that particular class. Here it specifies to use the element property to retrieve the coordinates, and doing so would give us a tuple of the elements. So using this, you can use the vector package in any mathematical situation, not necessarily limited to HEP. And these are the allowed coordinate combinations, so a lot of them. And if you enter any wrong coordinates, it will automatically error out and tell you which are the correct coordinate types. We can similarly use the NumPy vectors. So the NumPy vectors would be a structured array. So vector provides vector.numpy xt classes, so x for 2, 3, 4, and vector.array constructor can be used to create these NumPy classes. Additionally, vector NumPy xd classes can be also used to create these vector objects. And currently, vector only accepts structured NumPy arrays. These arrays have a D type of object, so they are not that fast as normal NumPy arrays, but we can create arrays of vector using NumPy. So this would create a vector NumPy 2D object with this being x and this being y, this being x and this being y for all of these, and the D type can be specified like this. So exactly identical to how you create a structured array in NumPy. You can then pass the same thing to the class, and it would create the vector NumPy 2D object. And you can also use pandas like columns. So for example, passing in a dictionary and specifying x and y values, and this should also create the NumPy vector as it was doing in the top two cells. Existing NumPy arrays can be viewed as arrays of vectors. So as these classes, vector NumPy classes, are these classes directly inherit the NumPy array. So the any operation that can be performed on NumPy array can also be ideally performed on these classes. And the existing NumPy arrays can be viewed as arrays of vector. But again, it needs to be a structured array. That is what vector can handle right now. So we can do this, creating a NumPy array and then viewing it as a vector NumPy 4D object. And similarly, we can use any, not any, but usually most of the NumPy methods should work on vector NumPy classes because they directly inherit the NumPy array. So reshaping it works as it would have done in the case of a NumPy array. We can then do a similar thing with momentum vectors, and it works as it is. So using the array constructor or using the momentum NumPy classes. Coming up to the awkward vector, similar to NumPy backend, vector also provides a vector array xd classes. So these classes inherit awkward array directly. So these classes are not mentioned in the this infographic here, but these are present in vector, and these are the ones that inherit awkward array directly. A vector provides two constructors to construct these classes, the objects of awkward vectors right now, which are vector.awk, or this can be vector.array. So vector.awk is just an alias for vector.array. And then we have vector.zip. So vector.zip acts as, so let me run this first. And this creates a vector array 3D with a jagged array with jagged data. So awkward allows us to create arrays of jagged data, which NumPy does not allow. So which is the data that HEP produces and which is that is required to analyze HEP data. Similarly, you can use vector.zip constructor, which is similar to ak.zip. Or another thing that you could have done was take vector.awk and pass in ak.zip with the contents inside. So this is what vector.zip does right now. Doing this would also create a vector array, which is a vector with jagged data inside of it. And similarly for the momentum vectors. And you can use the same properties that were being used on object and NumPy vectors. And additionally, you can also use awkward arrays, methods, and properties, because this directly inherits an awkward array. Going to vector.azimuthal, it would return an azimuthal awkward XY array. And then similarly, if you want elements, you could do elements, and it should return an array of elements. Vector.x would return the x value, and x would again be an array because our initial object was a vector of array, an array of vectors. Let's say if you don't want to use the vector constructors, you can do it. You can do the same thing with awkward.array, but in this case, you will need to register awkward. So here, vector would add all the vector behaviors to ak.behavior, and that would allow awkward to construct vectors just by passing a name here. So you could do with name 3D, with name 4D, and pass in the same parameters. This would work as well. And the same way as momentum vectors. Moving on to compiling vectors with Numba. So a vector also comes loaded with NumPyX backend. So right now, vector object and vector arrays are compatible with Numba, and vector NumPy is not compatible with Numba. At the time of writing vector, there was an issue that was blocking vector NumPy running on Numba, but now that issue is solved, and we hope to see a NumPy backend in the future. So, what Numba does is it pre-compiles or just-in-time compiles your Python code. So Numba ships LLVM, and it compiles your Python code. So it makes it faster. First, when you run the code first time, it compiles it and executes it. When you run the code second time, it executes from the compiled code, making it much faster. But here, in case of vectors, it would require you to actually have millions of vectors to see the effect of speed up. Otherwise, it might also end up being a disadvantage. Passing in the vectors in a function which is decorated by the decorator ngid, which is provided by Numba, it would make it possible to just-in-time compile that operations. And Numba only works with specific or a subset of NumPy and a subset of Python. So it is not, it cannot be used globally, but it can be used on a subset of NumPy and Python. That works as well. Computing mass. So we are passing into vector objects, and we're adding those vector objects and computing the mass. Now this would work. This would ideally work even faster the second time because Numba has already compiled this up. We can do the same with awkward, as we have an awkward Numba backend right now. Let's say we create an awkward vector using list comprehension. So we'll have a length of 50, and the inside data would be randomly chosen. The length of the inside data would be randomly chosen. So it would be 0 also, 0, 1, 2, 3, 4. I think, yes. So the first element is an empty list, and the length would always be 50 as we're specifying it here. We can then use vector.awk to generate a vector array object. So if I print this out, this would be a vector with, a momentum vector with jagged data, and we can print out the fields and type of it. So here the type means we have a variable length lists of momentum 4D vectors. I'll be touching it up ahead, and the fields just mean that we have 4 fields x, y, z, and t as specified here. Momentum fields that are labeled as x, y, z, and t inside of vector and upward. We can do the similar thing here, use the number and pre-compile this, second time compile this, and if we run it the second time, this should go much faster. And again, you would require like a lot of vectors or a list of like 1 million vectors to actually see the difference in speed while executing a normal Python code and while executing a number code. Moving on to a pipeline that uses uproot, awkward, and vector. So a brief introduction. Uproot is a pure IO library that can read and write root files. Awkward is the library that handles jagged data, which is like the NumPy for jagged data, and vector is the library that can create Lorentz vector, which are required in the analysis pipeline of high energy physics. We'll start by importing escape test data, which would allow us to download data from the GitHub repository of scikit-hep test data. So it comes loaded with a lot of different root files, which can be used inside your workflows. And we'll start by importing uproot. So looking at the keys of the retrieved data. So we have loaded the uproot hgz.root file, and we can look up the keys. We only have a single key events, and that events key corresponds to a T tree that has a lot of branches with a lot of data inside it. Now we can, this is a T tree with 51 branches. We can look at the branches here. So we can extract the actual data in the form of awkward arrays, and I've already introduced awkward arrays, and awkward arrays are fast. So they're not like normal Python lists. They are like the NumPy of jagged data. We can use trees.arrays, and again, like Jim mentioned in his talk yesterday, we can pass in what we want. So for example, if you want only fields corresponding to muons, we can do something like this, and it would only load up the fields that have muons, the fields dealing or the branches having the muon data. Let's load up all the branches right now, and let's look at the fields that we have. So we have a lot of fields. So if I had specified muon underscore star, it would have loaded only these fields. And I don't know about edmuon, but I think it would have loaded only these fields. Let's look at specific fields. For example, muon underscore px. Every field corresponds to an awkward array itself. So muon underscore px is an awkward array, and we can construct a vector using vector.zip and passing in all these awkward arrays as the argument or a dictionary values in the dictionary. So now we have a momentum array 4D. Let me print that up. We have a momentum array 4D object, and you can again go through the types, fields, and if you go through the type, so here 2421 star var means that we have 2421 lists of momentum 4D with each list having a variable. And then again, going through the same operations that we went through object vectors and NumPy vectors, we can also transform vectors to other coordinate systems. So for example, to rho phi theta tau, and looking at the fields, we'll have rho phi theta and tau. We can also in the dimensions by using 2vector3d, 2vector4d classes. So these all methods are listed in the readme of vector. And then we can slice these. So these are awkward arrays and a list of muon vectors. We can slice these as we want. The length of both of these are different. That means we do have a variable length list, and we could have also checked that from the type of this indexed object. As the first list had only one element, hence an index of greater than 0 should show an error. So here we would get an error because we're trying to access index out that does not exist or is out of bound. Let us create a mask which will select all events with 2 muons. So ak.nums provide would allow us to create a mask that would have that would filter out events which only have muons. We could have also done something like muons dot n muons, if I'm not wrong. If this was the field equal to 2, this would have also worked as well. And again, to go through the documentation, you can use the documentation to go through examples and how the method works. If you apply that mask to our original muons, we'll get all the events which have exactly 2 muons, and then we can filter out these events, these 2 muons events. So this would be the first muon, and this would be the second muon, using slicing the list in a 2D fashion. And then we can use methods from vectors such as delta R to compute actual physics. Let's say we do muon1 delta R, muon2. So compute all the delta R values. So if I print that out, it would again be an awkward array, and then we can plot this up. That shows up nicely. We can adjust the bins as we want. Yep, so this was a small example of how you can use vector with uproot and awkward in a data analysis pipeline. So we started by taking out the data using uproot, and then manipulating that data with awkward, and then converting that data into Lorentz vectors, using the muons and the events to using a mask to segregate events with exactly 2 muons, going through these events and choosing going through these muons and taking up the first muon and second muon, and then performing a delta R operation between them to generate another awkward array, and then we at the end plot it. So moving ahead, there have been some recent developments in vectors. So vector v0.9 is out, and v0.10 is out. So if you're using vector, you should upgrade to this version. v0.10 removes support for Python 3.6, and you can read more about these developments in the changelog of vector. There also are some future development plans for vector. So we are working on better constructors. Benchmarking suite is a possible future development plan. Then benchmarking against root. We will also be providing a complete awkward v2 support as soon as awkward v2 is released, which is scheduled for December. Then a NumPy number backend that I talked about, and other potential backends. So, and it was Vector's first major release was scheduled before PyHEP, but we couldn't. That was unfortunately delayed. A major release can be expected in October, which would be introducing the new constructors primarily. And again, you can reach out if you're stuck anywhere using GitHub discussions or scikit-app vector GitHub channel or the issue tab of Vector. I think that would be it from my side. I think it was a bit fast-paced, but I hope you got the gist of it.
Yeah, thanks a lot for this really nice notebook, and seems like it has been lots of progress, and it's really a great library, useful for many applications. There's one question from Eduardo and Slido. So he reiterates a work suggestion to make a phase-space work and profit nicely from vector.
We can definitely add that.
That's planned.
We can add that to future development.
Use fact I can talk. Yeah, it's nicely because when you generate simulation toy samples, if you can then manipulate them properly as vectors rather than just quote unquote random lists, it will be so much nicer, right? So that's actually something. That's what I mean. It closes the loop in something that is needed in workflow of what we have to do quite often. So if it's already on the to-do list, that's fantastic. Thanks.
Probably it's in the TensorFlow backend, right? That would make this happen.
Is that a phase space addition or a vector addition? It's unclear from your question.
I think it's just a bridge in the same way that we have the bridge now between decay language and phase space. I believe it's probably just a functional tool to be able to output. I think it's more of a phase space development in the end. So, but I thought I would mention here. Okay.
Okay, yeah. Then I think that concludes so far the session. And with that, we would go into a break until 16:30, if I recall correctly, and meet for the second session of the afternoon. So see you at 16:30.
Hi, everyone. Welcome back. I hope you all had a nice break, that little slot that we had. So we're going to get started with the second half of the session for Tuesday. And I'm very pleased that we have a speaker from the HSF training group, who's Alexander. And he's going to present the sort of the super condensed, powerful pill that you need to take to learn how to start to do plotting with Matplotlib. So I think with that short introduction, I can pass over to Alexander and let you unmute and share your screen, and we can get going.
Thank you very much, Grim. Can you hear me well?
Yep, I'm coming through very well for me.
Okay, thank you very much. And can you see my screen now?
Yes, that looks good.
Thanks. Yes, as Grim said, it's going to be super condensed. And on the Indico web page, we have different links. If you go to Run on Binder and click on that, well, it's going to take a while to open. So we're going to leave it there. In the meantime, there are other links. This setup link, which is has different options if you want to run this tutorial. So you can use Binder, or you can use Google Colab if you have any problem with Binder, or you can use Swan if you have access or you have a SEN account. For Google Colab, you need a Gmail account, and probably the easiest one is Binder. And or if you want to run the everything locally, you can just use Anaconda, and it's gonna work well. Also, there is another link here. This is Matplotlib for high energy physics, and I'm gonna go through that in a moment. But you can see also here the setup I just mentioned, and every episode or chapter of this tutorial. I'm not gonna go cover everything, but you can. This is publicly available, so you can access all this material. And the last one is the GitHub repo, which I'm gonna invite you if you see any issue in this material, you can contribute. It's not complicated, so you can open an issue here, or you just can open a PR, and we'll be happy to see any contribution from you. So I think this is still opening. Okay. Oh, it was fast. But it's okay. In the meantime, let me just introduce this tutorial. So this Matplotlib tutorial is based on the material that we have been developing during the last year in the HSF training working group. And this is going to be a very short introduction to Matplotlib, and I'm going to try to go through an analysis using some data from Atlas open data, and also from CMS to get some publishable plots. And if I have enough time, I'm going to go through PyHEP and Matplotlib wrapper, used in high energy physics as well. And again, this tutorial is going to be a subset of the complete Matplotlib training module. We already used this material last April in the first Matplotlib for high energy physics workshop. We had 100 students registered. And well, this material is constantly, we're trying to constantly improve this material. So again, if you want to contribute, we'll be happy to have you with us. So the expected knowledge is, if you have a beginner level understanding of Python, that's enough. Some knowledge of PyHEP modules is helpful, but it's not essential. And the idea in the first part, I'm gonna briefly introduce Matplotlib. And so the idea there is to get or to learn the basics of Matplotlib and learn how to manipulate the elements of a plot using Matplotlib. And then in the second part, we're gonna use Atlas Open Data, and we're gonna try to get this plot. And this plot is the plot for a golden channel for the Higgs decaying into 4 leptons, the Higgs decaying into 2 C bosons, and these 2 C bosons into 4 leptons. So the idea is to get this plot using Matplotlib. And then if I have enough time, the idea is to use MPLHEP and some CMS open data to get this plot, which is basically the same one here. Again, for the golden channel, the Higgs decaying into 4 leptons, the Higgs into 2 C bosons, and then to 2 leptons. So that's the idea of this tutorial. So let me go back to the binder. Okay, it's already here. So, okay, let me move this. Okay, and then we close this window. I'm going to open a new notebook here. And again, as I said, this is the material. It's publicly available. It's in the HSF Software Training Center webpage. So you can access this webpage, and you can have all the material here, and also all the people who are contributing to this material right now. So let's start with the setup. I'm sorry, the setup, no, with the introduction. And as I said, the idea here is to understand the basics of Matplotlib and learn how to manipulate the elements of a plot. So the first thing that we're going to do here is just to import the libraries that we're going to use during this first part of the tutorial. So we're going to import Matplotlib .pyplot, sorry, as PLT, and also I'm going to import NumPy. I'm going to use it later to generate some data. And then we're going to run this. So the simplest way to create a figure in Matplotlib is to use pyplot subplot, pyplot.subplot. So basically we have this. If we pyplot.subplots, and then actually if you run this, you'll, oops, sorry. Oops. Okay. Now, so what we get here is the area where we can plot whatever we want to plot. Okay, so that's how we create the space for the figure that we're going to plot. So let's use this data that we have here, and we're gonna see what we're gonna get. So 1, 2, 3, 4, and then we have this is 1, 4, 2, 3, and then to get the plot, pyplot.show, and then if you run this cell, you get this this plot. So you can see here we have actually, if you see the plot here, the first 4 numbers are the points on X, right? This is 1, 2, 3, and 4. Okay, so and the 1, 4, 2, 3 and are the Y points. 1, 4, 2, and 3. Okay, so of course we would like to plot different curves in the same plot, and we're going to see that in a moment, how we can get different curves in the same plot. So as I said, I'm not going to go through the details of many of these commands, but just let me show you here in this plot, because Matplotlib has something really interesting. If you see here, we have all the elements or the features that a plot should have, right? So the title, the names of the names of the axes. If you need these ticks, define these ticks. If there is a legend, if there is a grid, and for each one of these features of a plot, Matplotlib has a command. So we're going to see how we can use these commands to create a nice plot. So how we can work with these elements, or some of these elements. I'm not going to cover all of them. Again, this is very basic. You can do, Matplotlib has many features, so I'm going to cover some basics. So first of all, we're going to generate some data points. So we're going to call x1. We're going to use NumPy here to create some data. So with line space, we create these values or numbers between 1 and 10, and we're going to assign the variable x1, and then for y1, y2, y3, we're going to have the log of x1, and also the cosine of x1, and the sine of x1. Okay, yes. So actually, if you wanna check these values, for instance, for x1, these are the numbers for x1, or if you wanna see y1, y2, y3, you can see every one of them. So, and we're gonna plot. Now we're gonna plot these 3 lines. So we're gonna do again the same figure x equals PLT subplots. So we create the space in which, or the area in which we're gonna plot first the elements x1 and y1, and then we're gonna plot also x2 and y2. I'm sorry, x1, x2, x1, and then x1 and y3. And we're gonna show this plot. So this is what we have. So we have a plot with 3 curves, 3 lines associated to these values that we have, I don't know, created here. Okay, so next we're going to put the name of the labels of y and x. Okay, so I'm gonna work on the same one. So I'm gonna open some space here. So we have to put these commands have to be between the x.plot and plt.show. that's how Matplotlib recognizes that there is some information or some commands that have to be added in that plot. So let's say we would like to use we want to put the name of the labels of x and y. So for x, we're gonna use x.set x label, and we're gonna put here x values, and then for y, x.set y label. So you can see Matplotlib is quite descriptive in the use of the commands. So this is y values, and if we run this again, we have the name of the labels, of the labels of the axis. So if we want to change, for instance, the size of the text, we should put here as an argument, for instance, size, and I don't know, let's put here, for instance, 30, so we can see the difference. So you see for x values, it's 30, the size of the text. And you can do the same for the y values, for the y label. Also, we would like to put a legend. So we want to know, since we have 3 curves here, basically which one is which one. So what we have to do is to include here a legend. So here in the part where we plot every curve, we're going to put an argument, and just we're going to put label. And label is going to be the first one, which is this the blue curve. It's the log plot, or it's a log curve. The second one, it's going to be the label. It's going to be this is for cosine. Y2 corresponds to cosine, so cosine. And for the next one, the argument would be label and sine. And we have to add here another line, which is ax.legend. And with ax.legend, we're gonna get this nice legend here on that place. So we see that every one of them corresponds to every line here, every curve here. We can also, I just said that we can change the size of the text for the labels, but we can also resize and set the resolution of the entire plot. In order to do that, we should put here as arguments for the time of, for the size of the figure. We could put, I'm going to use the same values that we have here, so 10, 10, which basically corresponds to it sets the width and the height, which is 10 and 10 inches and 10 inches, and also we're going to use the DPI, which is the dots per, which means dots per inch, which is the density. And we're going to use 150. There is not any particular reason to use that, but so if we, okay, fixed size, I'm sorry, this is equal to, so you see the size of the figure has changed. So now it's bigger. So again, you can manipulate this as you want. If you want to have a smaller figure, or even more. But you can see that the DPI changed the density of the plot. If you compare this one, for instance, to this one, which has the original values. Okay. Of course, in a plot, we have to include the title of the plot. So actually, if you okay, let me put here the title, and it's again ax.set title, and then we put the name of the title, whatever title you want to use. So this is a figure with multiple lines. And then it automatically adds the title in this part of the plot. Again, you can change the size of the text. Just put in an argument here, font size. So if you want to change this value, just let's say just 30, and then you see the size of the text changed. Or if you want to see this in more detail, and but I think this is too small, or 20 is fine, or just by default the one that Matplotlib uses. Also, if we want to add a grid to the plot, we just put just add this command, and then we're going to have a grid in this plot. In addition to this, we can change the values of these ticks. So for instance, well, the Matplotlib generates this automatically, but you can change the values of these ticks. So for instance, just going to change these values. Actually, you can change the values. This Matplotlib generates these values automatically. But for instance, I want to, or I would like to see some specific values. So for instance, I can set the white ticks. The ticks on the y-axis, and let's put this. Oops. Let's put the same numbers, 1, 2, 5, 6, 7. So you're gonna see that the numbers here are gonna change. So now we have 1, 2, the ticks 1, 2, 5, 6, 7. And actually this is in a log scale in Y. And also you can change the numbers, but you can put some different labels. So for instance, let's put some labels to these specific values. So for instance, the first one, let's call it 1, 2, and we can mix, we can put integers and strings, and then we have 5, and then 10, well, then 6, this is whatever, and then the last one. So if you run this, you see that the labels of the ticks have changed. So you can play with all of this, and that's really nice. Matplotlib allows to do many things. These are just basic things. I'm gonna remove this, so just to get this plot. So for the last part, I would like to show you how we can change here. Matplotlib automatically generates these lines, continuous lines, but we would like to change the styles of the lines and probably use markers. So for instance, let me, I'm gonna copy this and put it here. And then we can use we're gonna add some lines, some line styles and some markers. In order to do that, we're gonna include those arguments here in the part where we plot these lines. So for instance, remember that the first one is this line, the log data. Then the second one is the cosine, and which is the orange one, and the green one is the sine. So we would like to change the log, and let's say we change this for line style. Let's say we would like to have this in this form. And for cosine, so we can differentiate even more these lines. And for instance, for this one, we use this. And let me see, for instance, for sine, we can use a marker. And this marker is going to be O. Okay, yeah. And actually, you can see here different, this is a table with different options available. So you can use whatever you want to use. So I'm using here this dotted line style. And also, well, there are many options. So you can play with that. And let's just run this plot, and this is what we get. So for log, it's the blue one. Is this this is dash line. For cosine, we have the dot line, and the green one is sine. It's a marker. It's the circle marker. So I think right now, I think it would be interesting if you can play a little bit around with this. For instance, try to combine, because actually you can change the color of every line. So there is a hint here. So since this is a tutorial, and the idea is that you can do something else, try to change the color of, for instance, the log curve using one of these options. So, for instance, you can change the color to green if you want to, or just to red. Is that an option? Yes, red. So try to do that in the next minute, and I'm going to do the same in a moment. So you're following, and I don't know if there's any question. I could try to answer any question if there is right now. So let me see.
There was one question in Slido.
Okay. I'm sorry, I cannot see Slido.
Well, in that case, I'll read it out to you. And it was somebody asking if the plot.show is necessary in Jupyter.
Well, actually, it's not. For instance, let's remove this plt.show, and then you get the plot, and then you get this message here. So in principle, it's not necessary. But I think this is a good practice to use plt.show, right? But in principle, no, you don't need it. I mean, you're gonna get the plot. But I think it's a good practice to use the command as it is. Okay, so for instance, let me show you. Let's change the color of the first line for red. So let's see. It didn't work. Oh, that's good. Oh. So let me change this. It's not. Oh.
I think you've mixed color and line style, right? So maybe if you just do the dash there.
Yes. Sorry. Thanks, Kilian. I think it was you, right?
Yeah.
And then red. Now it works. Yes. Thanks, Kilian. Sorry, I was mixing everything. That's good. Okay. So that's another argument. Also, you put this option in as another argument. So these are all the possibilities that you can have in Matplotlib. So again, this is a brief introduction to Matplotlib. So in the rest of this tutorial, I'm gonna go to the second part of this. I'm sorry, I'm moving this. So I'm going to go to this part and probably binder is all. No. Okay. So sorry, just let me remove this window. It doesn't allow me to see everything. So, okay, if you open binder and I'm working there, so you see there are some directories and there are some notebooks, and I'm gonna go through this one, which is the Higgs search, which corresponds to this chapter or episode. So I'm gonna open this one. I'm gonna close this one. And again, as I said at the beginning, if you, for any reason, have problems running this tutorial with Binder, you can use Colab, Google Colab. There is a link, there's a badge here, so you can click on that, and then it's gonna open. Just be careful. Google Colab has some libraries, but unfortunately it doesn't have the libraries that we use, so you have to run some commands before you start to work. And also remember that in Google Colab you need a Gmail account. So I'm gonna, for this part, let me go through this okay, I think it's better like this. So I'm gonna go through this notebook, and just because of the time restrictions that we have. So as I said at the beginning, the idea in this notebook is to use some Atlas data collected during 2016 at the Center of Mass Energy of 13 TeV, which is equivalent to 10 inverse femtobarns of integrated luminosity. And okay, and this data corresponds to the data available of the golden channel, the so-called golden channel. So we have the Higgs decaying into 4 leptons, the Higgs decays into 2C bosons, and these 2C bosons decay into 4 leptons. So this is the decay of the standard model Higgs boson. And here we have, or we will use the data available for final states with or samples with final states with 4 leptons, and also for simulated samples and data. And we're gonna see how after applying some cuts, some selection, we will see the invariant mass peak of the Higgs boson at the 125 GeV, and that we, or the LHC, Atlas, and CMS observed in 2012. So again, as usual, we need to import the libraries that we need to use here, which are going to be pyplot and NumPy. So we can run this line, and the samples that we're going to use, actually, if you go through this directory, you see there are two directories. And the first one, we're going to use the first one. So we're going to have here these 4 files have data with 4 leptons in the final state. And then we have some Monte Carlo data. So we're going to use these files. Let me go back here to this and then close this. Okay, so the first thing that we do here is to create a dictionary with the samples that we have, and actually we're going to use the 4 data samples, A, B, C, D, and the Higgs Monte Carlo samples, which are here, and all which are here. Sorry, the Higgs. This is for the data samples. This is for the Higgs Monte Carlo samples, and this is for the CC Monte Carlo samples, and this is for other Monte Carlo background components that we have. All of this is in that directory that I just showed you. We're going to use uproot here to read the content of the samples. They are in root format. Actually, if you saw this part here, they are in root format. So we're going to use uproot to read the content of that of those samples. So if we run this, we see that every one of these files has this information, actually branches or variables in every file. So we import uproot, and then for each sample of the dictionary that we created with the data and Monte Carlo samples, we will return another dictionary, and these dictionaries are going to contain the branches or the variables of every file. So this is what we get here, and samples. Okay, let me run this again and see. For some reason, didn't work. Okay, now it works. So let's look at the branches that are stored in the first file in data A. So we have here 18 branches, or 18 branches or 18 variables. And let me see, we can see or list the keys of this data. So we have the number of leptons, the mass of the 4 leptons, weights, and good leptons. We're gonna see that later. Channel number, lepton PT, good leptons, cross section, a lot of information. So with this command, let's try to access on one of these branches and make a simple plot with that branch. So we run this, and then we're going to use the pyplot hist to get the histogram, so we can visualize the distribution of the mass of the 4 leptons. And this is what we get again. PLT, for some reason it's not. Let's see. it is not defined.
I think you need the from matplotlib.pyplot import or import matplotlib.pyplot. Oh, okay, it's there.
Yeah, it's here, but I don't know, for some reason.
I think you didn't execute it last time. I think if you just click, you just execute the first one again. This one.
Yeah. I did that. Okay, let me do it again. Actually, that twice already.
Yeah.
Let me see. And now it's okay. Yeah, I don't know. For some reason, it's weird. Okay, so here we have the histogram. This is the mass of the 4 leptons for the data A sample. And well, we could do the same for different branches, or if you want to take a look, or for different data. You're gonna play with that a little bit. So again, for instance, here, as we just saw that, you can change the size of the text. You can include here the labels, the y-axis, the x-axis, and you can play with that a little bit more. So, and actually there is an option here in which you can change the font size and the font family, and you can put this as a global setting. So actually it's gonna change everything from now. So we're gonna use it. We can get the same histogram and see the changes. So you can see this was the first one, and then we just we just resize the plot, but it's the same one, a little bit bigger. Again, you can manipulate and play these plots as you would like to. Okay, so let me go to the selection criteria of the plots. I'm sorry, the cuts that we apply here. That can apply here in the data and in the samples and the Monte Carlo samples. And the reason to do that is that with these cuts we are able to select the events that are that are of our interest. So it's going to be a subset of the original samples. So these cuts are going to change the distribution, and this is going to help us to do some physics analysis, and of course to search the physics process that we are interested in. So in the case of this 4-lepton final state, the selection or the selection or the cuts from all the samples should satisfy this criteria. The leptons need to activate either the muon or the electron trigger. The number of leptons in the final state should be 4, and the reason again is that the Higgs, we're looking for the Higgs into 2 C bosons into 2 leptons. The total net charge should be 0. The good leptons with that high transverse momentum. So we can visualize some of these requirements, and we're going to continue working with the sample data A. We can see, for instance, with this is again using uproot, how many good leptons we have in this event. So we go to the branches of data A, a good lepton, and then we get this okay, but then we can see that some of them don't satisfy this selection criteria. We have here 4 leptons, but for instance here we just have 3 leptons, Actually, we can see that here the sum of good leptons. So for instance, we have 4, 4, 3, 4, 4, 4, 4, 2, 2, 4, 3. So we need only the processes in which we have only 4 leptons in the final state. So we can select all those events where the sum of leptons is equal to 4. Okay. So now, in this part, I'm not going to go through the details. Almost almost running out of time. So in this part, we save in a dictionary all the requirements, or for all the samples, the requirements mentioned before. So the selection criteria are included here, or the codes are included here. I'm going to just run this. Again, if you are not going into the details, you can go through this material, but sorry, we cannot cover everything here, but, and we can compare. This is quite interesting. We can compare the number of initial and final events after the selection. So in this case, we have the initial events. And here we have the final events. So again, when we apply the codes, we would like to reduce the background events. And what we would like, what we want to do is to keep the most of the originals, or the signal that we are interested in. So as you can see, the selection for the background events are reduced after the selection, and these are in percentage. And let's see, let's plot the Monte Carlo samples. In order to plot the Monte Carlo samples, we will do stack plot. So the Monte Carlo samples are associated to the C bosons, the CC and other that I showed you at the beginning. And we have to take into account the weights, which they include important information. They modify the Monte Carlo. I'm going to go through this very quickly. And this is just to check the lengths and see that everything is okay. And this is what I'm going to run this quickly. But this is the plots that we would like to get. Monte Carlo samples without weights on the left and with weights on the right, including the Higgs, CC, and the CCC bosons and other channels. So, so you're gonna see here 2 bombs around 90 GeV, and another one at 125 GeV. The one corresponds to the mass of the C boson. The second one would correspond to the mass of the Higgs. Without weights and with weights. So, just to end this part, just let me run this part, and I just want to get to the final plot. But here we just take the values of the masses of the 4 leptons in every data sample in A, B, C, D. Remember that we were using only the data sample of A, but we have to include all of them, A, B, C, and D. And again, this is just to check the length of the list, if everything is okay. And we want to include uncertainties. So we need to, we would like to do, to include error bar functions. And finally, we're going to include the Monte Carlo and the data in the same figure and see if they're in agreement. They should. So this is the plot that, yeah, this is the, sorry. This is the plot where we have all the Monte Carlo and the data. Sorry, I'm going to try to reduce the size. See if we can have everything. We can see this. Okay, much better. So we have the number of events here, the mass of the 4 leptons. Remember the Higgs decaying into 2 C bosons, and then the C bosons decaying into 4 leptons. So here we have the data, and the Monte Carlo here also. So again, you see 2 bonds, one in around 90 GeV, which corresponds to the mass of the C boson, and another one around 125 GeV, which corresponds to the mass of the Higgs boson. Also, well, we can get this plot in a more just another format. But this would be the final plot that was the idea to get. Again, using Atlas Open Data for the golden channel, the Higgs boson decaying into 4 leptons, and that was used to observe the Higgs boson in 2012. Unfortunately, and I knew it, I don't have enough time to talk about the MPL-HEP. But again, you have access to all the material if you want to go through that in detail. As I said at the beginning, we use this material for the Matplotlib for High Energy Physics workshop. And this workshop, well, in April, it took a day and a half. So I tried to super condense many things in 1 hour, or well, less than an hour, 50 minutes. And but again, you can go through the material. If you see any issue, you can contribute. You can go to the GitHub repo, open an issue, or just open a PR, and you can join us. We meet on Mondays, the HSF training working group. We need people to keep developing these materials, and also, even if you don't have a lot of experience, you can contribute. And also just stay tuned. We're gonna have soon the second version of this workshop, the Matplotlib for high energy physics workshop. So you can participate, and you're gonna see all of this in more detail, and also you're gonna have time to practice, which is quite important here. So I'm gonna leave it there. I think it's time. So I don't know if there is any other question or comment.
Yeah, thanks a lot, Alex. That was a bit of a whistle-stop tour, but I think you managed to get a lot in that people will want to have a look at themselves in practice as well. So there's at the moment there's no questions in Slido. So if you've got one that you would like to put in there, just type away. If not, you can also just raise your hand, and we can take a question.
Yeah, I'm sorry, I don't.
That's okay. I'm watching.
Yeah, sorry.
I'll let you know. Yeah.
Yeah, that's a problem with Zoom. You cannot see anything else. So
that's right. If
you can, but
yeah. I mean, maybe I'll make a comment myself. I mean, just to ask you a question. So there's obviously the experiments develop a lot of experience, and for instance, root plots, which are absolutely the standard way of doing this at the moment in HEP. They're kind of like libraries of styles that you apply for this font size and this, italicization and so on and so forth. You showed us very much how to build a Matplotlib plot from the ground up, which I think is great because it gives you a lot of insight. But are there also like libraries that people have done just to apply a set of standard settings and just get kind of nice plots that you can generate quickly without having to type in every single formatting detail of the axes and the legends and so on and so forth?
Yeah, that's true. Yeah, again, the idea here is just to, since this is the material has been designed to be applying this workshop, which is it's an introduction to Matplotlib, right? So the idea is also to especially for the students to to sit down and type everything.
Yeah.
So that's you learn, right, when you do it by yourself. So even if you don't, you can use then libraries where they do everything for you, but again, I think it's good just once in your life to sit down and type, right?
Do it top to bottom. Yeah. Actually, Eduardo and Killian have just pointed out that this is, of course, is exactly what MPL-HEP is there for, to have the standard styles for the LHC experiment.
Yes.
And I want to add that this is actually part of the Matplotlib module. So the part that Alexander just taught really nicely, that's like the vanilla Matplotlib version. And then in one of the later parts of this lessons, we switch over to MPL-HEP and show how you can get this consistent style with just one added line for all of your plots to really make this convenient.
Yeah. Okay, and a couple of questions appeared in Slido as well. So the first one is, how would you represent PDFs that are not histogram templates? For example, when you have the function itself, is it easy to stack those representations?
Oops. I really don't know how easy it is. Actually, we had to, the files that we are using here, we had to filter them out because there were a lot of information, and for the purpose of the workshop, we don't need that much information. So to be honest, I don't know, but I think it would be interested to see that and see if we can add that to the material. I think that's
right. Okay, that's
great.
Again,
if there are ideas like that, we will be very happy to have your help. I mean, I think Killian is asking for the slide. Okay. Yeah.
Okay, I mean that's probably a discussion we can also continue offline and in Slack as well. And then Eduardo was just asking if you had example analyses from LHCb as well. No. Not yet. Okay.
No, we have Atlas and CMS.
Right.
Yes.
But we'd happy to have like different options there to maybe switch between them. But then again, I mean, for the plotting, it should be very simple, especially because the styling is easy to switch out with MPL-HEP. So maybe for this lesson, it doesn't matter all that much.
Yeah.
Agreed. Thanks.
Okay, thanks, Killian, Eduardo. Okay, thank you very much, Alexander, for that tutorial. It was very interesting. Let's move on to the last presentation of the day, which is on conversion of a production-grade Python CMS analysis to distributed R data frame, which is obviously the new interface and route for managing analyses, and the distributed part of our data frame is an exciting new development. So we're very happy to have this contribution. Tommaso, I see you've turned your camera on, so I think that answers my question as to who's giving the presentation. So I'm guessing it's you.
No, we will split the presentation. Vincenzo will go first.
Okay,
he also switched on the camera.
Well,
so
then I let you guys. I just saw your lovely blue background first. Then I let you guys share the screen and take it away. We have half an hour in total, hopefully. So hope for some time for questions as well. Thanks, guys.
All right. Thank you, Graham. So I'll just start myself. Let me know if you can still see the slides if I open them full screen.
Yes, they look grand.
Perfect. All right, so let me start then. Today we are here to share some of the experiences that we had in converting a production level CMS analysis to from a more traditional approach, let's say, to distributed R data frame. And this is going to be completely written in Python. You'll see more details about that. So I will start. My name is Vincenzo Padulano. So I will just introduce the objectives of this joint effort between root team and some of the guys from the INFN group. I will describe some of the features that were specifically developed within our data frame for this effort. And then I will give the floor to Tommaso to talk a little bit more in detail about the analysis facility that was set up to test the tools, some of the performance that we could measure. And then finally, we'll finish the talk with a demo of what we did. So let me just start by saying that this is an R&D project, a little less than a year. We've been trying to improve or at least research on some of the new approaches that we can use for data analysis. In this case, it's going to be specific for the CMS analysis, but all of the things that you hear today about the tools, the approaches can actually be quite generic, quite more generic. And although it's an R&D project, as I said, it is very much usable already today. So hopefully you'll be interested in trying it out, maybe on other hardware than what we have used and other analysis types. So the general idea, of course, is something that can be quite something that is quite natural. Let's say the continuous optimization and improvement of our workflows. And nowadays, and it will be even more so in the future, this means a very heterogeneous type of platforms, from single core or many core computers to many nodes in the same computing cluster. But we want to make the experience as easy or as streamlined as possible for the final analyst, from 1 core to 1,000 cores on different machines. From the user perspective, this usually means running an analysis on billions of events in CMS, and especially in this case, we are going to discuss the processing of nano-AD data format, but this is again quite generic. It used to be that one needed to submit thousands of single core jobs to the grid, and then resubmitting those jobs that were failing and then merging them. There were multiple steps involved in this workflow. We'd like to see some way to just streamline all of this in a tool that is interactive, and at the same time takes away all of those responsibilities from the users. And when we say interactive, what we actually mean is being able to use a simple interface, but with the full power of, in this case, a tier 2, so multiple machines that can still run the computations in a transparent way that is kind of decoupled from the actual interface or the machine where the analyst starts the analysis or writes the analysis. At the same time, we still recognize that the batch features, so the batch systems are there, and the resources that they can manage are totally necessary for this type of analysis. So it would also be very nice to finally have some infrastructure that is flexible enough to accommodate both the more interactive use cases and the more batch-like approaches. And this is one step towards that kind of approach in general. As far as the analysis tool is concerned, we think that distributed R data frame can be one such analysis tool that allows all of the requirements that I just described. And in particular, let me just give you a recap. R data frame itself is the main analysis interface that root offers nowadays. It's been in production for a few years now, and its usage and description are out of scope for this presentation. So I will just move directly to saying that there is a distributed layer for our data frame, such that all of the responsibilities of creating the jobs, splitting the input data set into different chunks that are then processed by all jobs, and the merging of the results and sending the result back to the user, all of these features are integrated in a single Python layer that takes care of running the our data frame C++ event loops inside of the computing cluster. These can run currently with either the Spark or the Dask schedulers. And this means that within a single API, which you can see sort of sketched here on the right, you will see more details later, a user has access to multiple types of backends, both from the scheduling point of view and from the cluster management point of view. In particular, Dask is quite popular, has gained quite some popularity because it has very nice interaction with batch systems like Slurm or HDConder. So that's also a very nice addition. Some of the things that were specifically developed for this effort in the distributed part are, for example, the fact that distributed R data frame jobs are flexible enough to understand whether a certain task will actually have to process some entries or not. In the cases a task doesn't need to process any entries because, for example, in the data pipeline, some of the files, some of the input files for the analysis were previously skimmed and they led to empty files. Then the actual R data frame task becomes a no-op. So there will be no extra usage of resources on the cluster. The task will just stop. So only the tasks that actually have to do something will process the data set. And this was crucial also to, in general, as a distributed engine, this is crucial to have some flexibility in the kind of scheduling that you can drive to the computing cluster. Together with this, a whole lot of other R data frame operations were added to the distributed layer. Here I am listing them. There's define per sample, there's redefine. And then there are two, let's say, maybe more common or more important ones that are the systematic variations and the possibility to run multiple R data frames concurrently, distributedly in this case. So let me just say a few more things about those two. The latter one, it's called run graphs. You can see an example snippet here. The run graphs operation, which is already available with the traditional R data frame, means running multiple R data frames concurrently. In the distributed case, it means executing or launching the distributed tasks of two different R data frames that can process different operations on different files at the same time. So instead of launching only the jobs of one R data frame and then the jobs of the other one, you launch all the jobs together at the same time, and then the cluster scheduler will take care of running them within the resource limits. And finally, systematic variations, which were added to traditional R data frame in the last root release, have also been added in the distributed version for the purposes of this work, and they will thus be available in the next root release. In both cases, for the variations, systematic variations effort, and for the run graphs that I just described, one of the nice features of the distributed layer is that the API doesn't change at all. So you will be able to run your R data frame analysis as it is currently today, but in a distributed environment with no extra code change needed in that sense. Finally, just a final thing to say for the purposes of this study, we wanted to gather all the metrics possible about the resource usage. So now inside of the R data frame task, there are automatic logging there is an automatic logging systems for metrics such as CPU, network, and memory, so that these can then be more precisely evaluated after the execution of the distributed graph. So with that said, I will just stop sharing my side of the screen, and then I will leave the floor to Tommaso for the rest of the presentation.
Thank you, Vincenzo. Can you see the slides? I think I am full screen now. Can you see? Can you confirm?
Yes,
yes,
yes, I can.
Yes,
okay, okay, thank you. Okay, so as Vincenzo said, I will talk about the actual infrastructure and the use case that we use to test this infrastructure, and the infrastructure served as a benchmark for this analysis. So first of all, the infrastructure, the NFN facility that has been built up is built upon three main building blocks. For the user, to manage the user-facing part, we use Jupyter Hub and Jupyter Lab. So the user access the Jupyter Hub and then works within a Jupyter Lab session. Then he can access the resources via Dask. So Dask introduces the scaling over a batch system, which in this case is htconda, and that access is provided via XRD protocol. Since at CMS and INFN, the topology of the resources is distributed and pledged, we try to integrate everything and possibly even opportunistic and private clusters as resources. But this is not a user issue. Basically, everything is hidden behind a single hub, and so the user doesn't have to worry about grid, the difference between running on grid resources, cloud resources, and so on. So in principle, the resource could be a cluster, a single fed node, a cluster of fed node, and so on. So this is the infrastructure that we use, and the use case that was mentioned before is a real VBS inside WW analysis with an hadronic tau and light lepton in the final state. This analysis uses NanoD inputs, which are CMS-specific format that are basically plain root files. And this analysis was firstly implemented in with a legacy approach, so meaning using NanoD tools and PyRoot-based scripts, and was ported then to distributed R data frame. The aim was to achieve enhanced user experience and improved efficiency, and to optimize the workflow and the operations on data. As Vincenzo said, there was a continuous collaboration between the INFN group and the root team in order to implement, to test and implement the needed the data frame features needed to streamline a full-scale physics analysis, and then to evaluate the performances. Talking about some details, the analysis, this analysis is can be split into different parts. The first part is a part that in the legacy approach is run on CRAB, so on grid resources, using NanoD tools, which includes a scheming based on triggers and a first preselection of the objects, and then the computation of all the necessary corrections. The second part is run in the legacy approach on htconda at CERN at Helix Plus, and uses plain PyRoot scripts plus some utils from NanoD tools. And the event loop on events is run for each systematic variation. Then it comes the merging of the results and the histogramming. Those two parts were ported to distributed R data frame, and so they are both run on the INFN analysis facility. So using a Jupyter notebook basically, and so running on the resources that I mentioned before. And thanks to the advanced feature that Vincenzo mentioned before, the systematic variations and the merge steps are all done automatically in a single event loop. So here is how it looks, an analysis code in distributed R data frame. Basically, you have first an initialization function where you have to declare all your C++ function that do what you want in the analysis. Then you declare you define your R data frame with your distributed R data frame. And then you go with your analysis, so with a bunch of defines and filters. Finally, you save your results with a snapshot, or you get your histograms with a histo1D method, and you can also inspect the data using display. So the parting targeted these functions that are used in the analysis, which are, as I mentioned, the C++ function that manipulate RBAC objects. If you want to introduce the variations, it is trivial. You have only to insert the vary statement in the analysis, and then do the variation for command, and that's it. So we monitored the task execution. So thanks to all the features that were implemented, we were able to look at all the performances of the code, basically. So as an example, we took the pre-selection part, the pre-skimming part in a distributed data frame, and then we can have a look at the CPU usage, the memory usage, and also we set up a monitoring for the network RED. In order to have control of everything, basically. Basically, we took as a benchmark the analysis of a part of the run to Monte Carlo that we use in the analysis. In particular, we use 1 year, the 2017 Monte Carlo Ultra Legacy, which is 1 terabyte worth, and basically, we looked at the increase in terms of speed up of the analysis, overall speed up in terms of time, and basically we are getting something of the order of 10 times what we achieved with the legacy approach. So, in order to be concrete, we will see a short demo. I will show a short demo that shows how we access the analysis facility, how we set up the Dask cluster, and then how we run a notebook with analysis code. It will be a very simple example, but it's just for showing the workflow, let's say. So I will be very fast. So first of all, we have to go to the proper endpoint, basically, and log in with the CERN single sign-on. So once you logged in, you have to spawn your Jupyter Lab session. In this case, I will use my custom image. And everyone is free to use its own image and choose the resources to be deployed. So now the container is starting, and soon, in a matter of tens of seconds, we will be able to get access to the Jupyter Lab environment, to the Jupyter Lab session. And basically, we will first deploy the Dask cluster on the distributed resources. Then we will run the analysis and get the results. So we are automatically redirected to the Jupyter Lab. First, to deploy the Dask cluster, we have to go to the Dask extension and click on New. Here you can choose the resource the tier, the resource that you want to use to deploy this. Basically, you have to choose which HT Condor pool to use. In this case, we will use the tier 2 resources at Legnaro. So by clicking on Create, you basically are launching, submitting a Condor job to that HT Condor pool. In fact, if we look at the Condor queue, we will see that there's an idle job, and this idle job contains the Dask scheduler process. So as soon as it goes running, here it is, we will see here the connection starting. Here it is. And then we will be able to see the dashboard here with all the important tabs important tabs to see the status of the cluster. Here it is. So let's have a look at the workers tab. Here we can see basically the number of workers and their CPU and memory status and other important info. But now, of course, the DAS cluster doesn't have any workers. So we would like to scale it. We will do this with this button. So we choose 10 for this example. And now we can see here that there are some other Condor jobs that are sent to the HT Condor pool that contains the worker processes, of course. So as soon as they go running, we will see here the number of workers, the proper number of workers. So now they are running. So if we go here, we will see in some seconds the total number of workers. So here they are. Okay, now let's retrieve the analysis code that I pointed out in the slides, which is this one. We will do a very short, a very simple analysis. A very simple analysis which uses CMS Open Data, Monte Carlo, W plus Jets samples in order to get and doing a VBS-like analysis, but is only for example purposes. So here in the notebook, we do some basic imports and some basic definitions. I will come here later. Then here we do we define the initialization function, as I mentioned before, declaring including the utils.h file, which contains all the necessary functions. Then we connect to the cluster, and we declare to our data frame the initialization function. We define the chain of files that we are going to analyze, and here we do the analysis itself. So first of all, we define their data frame, then we define a dummy variation in order to show how it works. Basically, it is only scaling this variable. And then we do the selection of two jets, a muon, and a tau, basically, and then we compute the invariant mass of the four objects, and then we do the histograms. The histogram of this, we create the histogram of this variable. More specifically, we will create the histograms for all the variations. So we will have the nominal one, the variation up, and the variation down, and we will plot them. As you can see here, we will redo this, of course. We'll plot in the same canvas just for example purposes. So in order to be able to run this, we only have to set the correct scheduler port here. We only have to look at this number. So in this case, it's 21528. And then we have to choose the number of tasks to be sent to Dask. In this case, we have to choose, a good practice is to choose 3 to 5 times the number of workers that you have. So in this case, 50 is a good choice. So we launch the execution, and we go and see some useful tabs of the dashboard to look at the execution. So the progress one, the graph one, and the end processing. So let's go first with the graph one. The graph one shows basically the MapReduce structure of the computation. So these are the mappers and the reducers, and then you get the results here, of course. Here instead you have the process, so you have the progress bar of the execution. You can monitor how many workers, how many tasks have been processed and are still to be processed. And finally, here you can have a look at how many tasks is running each worker, basically. And that's it. This is evolving, of course, and you can see here that the CPU usage of each work. So as the computation goes on, memories are released, or results are kept in memory until they are released. And finally, we will hopefully see the computation over here, and we will get the results back in the notebook. Let's be patient for I think 5 seconds, 10 seconds, more or less. And once the computation is over, we shouldn't see anything here, and we have to go back to the notebook to see the results. So three main reducers left. Here they are. So the computation is over. And then if we go here, we see that each color corresponds to a different variation, different varied histograms. And so we see the 3 histograms varied. And basically that's it. This is the workflow of the analysis code, the real analysis code that we use for the analysis. Coming back to the conclusions of this presentation, basically there are some lessons that we learned during all of this. Basically, we can say that the transition from legacy to distributed R data frame looks reasonably easy. Also thanks to the advanced features that were introduced recently, for example, the systematic variation. Another great added value is that you can do what you do locally, distributedly, with almost no effort, seamlessly. The same code works for both the scenarios. There are some issues with the debugging, meaning that there are occasional task failures that are not well understood because there is no clear error pattern. Besides, if you want to take everything, to have everything under control, you have to monitor the resources in order to understand if there are possible bottlenecks or errors. Finally, we also use machine learning in our analysis. More specifically, we do inference. We do the inference with an external DNN model trained with TensorFlow. In order to use this external model, we need to go via ONNX files. So you have to move from TensorFlow format to ONNX format, and then use the TMBA SOFI engine. And basically, that's it. Thank you very much. If there are any questions, we are here. Thank you.
Hi, Tommaso and Vincenzo. Thanks very much for that presentation. It was really interesting. It's so great to see that scaling in practice. There are a couple of questions that we have. So the first one is from Michael, who's asking, how does this approach compare to using the Swan service at CERN? So I guess that's the infrastructure backend. Michael says, I'm not terribly familiar with it, but it seems designed for similar use cases.
I think Vincenzo can answer better than me. I think he's more experienced than me on Swan, but basically the interface is the same, of course. The resources, I don't know what resources are available on Swan. The great added value here is that you are integrating resources distributed geographically. And so this is a solution that could be different, which means that the task scheduler is deployed on the resource that is distributed, is geographically distributed. I don't recall the resources that are available on Swan.
Yeah, exactly. So there are differences, let's say, at the infrastructure implementation level, but I would argue that it's not the point. I think the point here is providing this kind of interactive interfaces to users The one that has been developed within the INFN group is valid, and it has a direct connection to grid resources that are managed by INFN. In general, the theme of analysis facilities is a quite popular one now. There are analysis facilities coming up and being developed and constructed. Swan is, let's say, one analysis facility. The important thing is that we or let's say the community can share the approaches, the interfaces, so that users can see, let's say, a homogeneous universe where they can run their analysis from some hardware to other hardware. I would say the actual implementation of the infrastructure is, let's say, secondary, as long as the software tools are able to cope with all the requirements that the users have. On that note, distributed R data frame already runs on Swan because it's available via the LCG releases. So if you have access to Swan, you want to try it out, feel free to do it. And if you want some help, you can also reach us on the root forum or on the Mattermost channel. So I would say that's definitely something very, very flexible.
Another question, if I could, then we should close to go to the social time, right? Just one final one. How widely used is the workflow in CMS? Michael was asking.
Sorry, how wide?
How widely used is the workflow? So how are you getting along, attracting more people to try it out and see how it works for different analysis, maybe different workflows?
This is I think this is the first attempt to do this like this. Let's say I am aware of other analyses that tried to implement some part of the analysis in our data frame. Distributed data frame is quite new, as if I recall well. So it's something that is being tried for the first times, I think, since 1 year and a half. Correct me if I'm wrong, but so there were some attempts, but this is I think the first time that we go end to end. So everything, every step of the analysis is. There are other tools that do this in CMS that are based on our data frame, but these features that we are using are brand new. Let's say. So it's there were some attempts, and there are well-established tools that use our data frame, but all these new features are brand new. Let's say they were developed for this not only for this use case, but driven by this use case.
Yeah, in that case, it's fantastic. Yeah, quite impressive actually. Thumbs up on this. So yeah, in the interest of time and just for people to socialize a little bit, let's close it here and please take any questions to Slack as usual. So let me thank everybody for the session today. There's been a great second day again. If you still have a bit of clock cycles on time, go and socialize. So you can just click and wait. Unless otherwise, maybe see you one of the next few days, and maybe even tomorrow. All right. Thanks again, everyone. Bye bye.
Thanks a lot. Bye.